If space is a stage and time is music, then who wrote the script for the universe? That question arrives like a single, clear note struck in a cathedral of silence. It hangs, resonates, and draws attention not so much to what can be seen, but to the shape of the silence between things, the empty measures that make melody meaningful. It is the kind of question that has never been merely intellectual for humanity. It is emotional, existential, stubborn. It insists that the observer pause, tilt the head, and imagine an author, a mind, a pattern, a cunning that arranged stars and seasons, cause and consequence, chance and constraint. And yet it also prods the opposite intuition. Perhaps there is no author at all, only the slow, patient choreography of blind laws that, when left to their own devices, pull forth order from chaos. This first part is an invitation. It is not a claim. It is a doorway opened onto the long, dim corridors of deep time, into a hall where records are fragile and erasure is the default. It asks the listener to suspend certainty and consider two parallel impressions at once, that the universe feels designed, and that design may be an illusion cast by patterns of repetition and selection. The tension between these impressions is the heartbeat of a larger curiosity, the desire to know whether the script exists and, if it does, whether its lines are legible. Across cultures, across epochs, humans have responded to the question of authorship with stories. Gods drew maps, ancients carved commandments into stone, philosophers argued for the existence of laws written into the fabric of reality. Those responses comforted and guided, but they were also attempts to translate complexity into narrative, an author explains. A plot orders, and a purpose redeems randomness. In the modern age, the author took on new forms. Laws of physics, equations on chalkboards, dark matter halos plotted in false color maps. These became the new scribes. Scientists, in their laboratories and observatories, deciphered patterns and translated them into predictive sentences. The language changed, the impulse did not. But there is another, quieter impulse that often goes unremarked in the rush to explain, the fear of permanent loss. Deep time is not merely long, it is a slow solvent. Rocks, metals, whole cities, even mountains are subject to processes that obscure, transform, and ultimately obliterate. Rivers grind stone into dust. Tectonic forces fold and bury. Chemical weathering dissolves inscriptions. Biological life consumes what is brittle. The deeper the time scale, the more thorough the erasure. What is preserved is rare, accidental, or stubborn. This means that the physical traces of many plausible pasts might lie invisible to an observer anchored in a shallow present. Imagine a civilization that rose and fell across a few thousand years, built of perishable materials, centered around practices that left only faint chemical footprints. Over 1,000,000 years, wood ruins rot, metal corrodes, and even stone structures collapse and are recycled into new geologies. After 10 million years, the only potential signatures might be anomalies in isotopic ratios, tiny concentrations of synthetic polymers embedded in sedimentary layers, or an oddness in the global distribution of certain elements. Even these signs can be masked by volcanic upheavals, oceanic circulation, or the metabolic work of life itself. So the question of an author of the universe becomes entangled with another question. Who, or what, can write a script that survives the slow editing hand of geology? The Earth is, in its own right, an archivist with selective memory. Its pages are sedimentary strata, annual rings, trapped gas bubbles, and crystalline lattices. Some pages are kept in meticulous order, the ice cores recording atmospheric composition, the layered deposits preserving sudden events. Others are rewritten so thoroughly that they read like blank parchment. Human civilizations have been excellent at leaving ephemera, plastic bottles, nuclear isotopes, microplastics in the ocean. These are obdurate marks, the modern equivalent of a signature on a syllable of wet clay. Yet even the durability of plastics is finite on geological timescales. The present, in other words, might write loudly for a while and whisper, eventually, its volumes consumed by slow entropy. This awareness introduces a kind of humility into speculative thought, the recognition that absence of evidence is not evidence of absence. An archaeological silence across deep time can mean many things. It can indicate that no one ever wrote on the page. It can indicate writers whose marks were ephemeral or intentionally subtle. It can mean that the script was in a language now unreadable to an observing intelligence. Or it could mean that the script was written so long ago that the planet has repurposed the ink into stone. If the script exists, how might it be structured? The mind naturally imagines a few archetypal possibilities, each with different implications for the types of evidence an observer might find. First, the script is law. In this archetype, There is no separate author in the sense of a conscious agent who planned the universe. Instead, the script is the set of fundamental regularities, the constants of nature, the equations that govern matter and energy. These are not authored in the human sense. They are the grammar of existence. When space is stage and time is music, the laws are the architecture of the stage and the rhythm of the score. They set the range of possible stories. In this view, the appearance of complexity, galaxies, life, and civilization is an emergent property of the grammar. An investigator seeking authorship would find remarkable regularity. Signatures would be mathematical, invariant, physical constants, symmetries, conservation laws. The evidence would be in the reproducibility of phenomena across space and time. It would feel, to an observer, like encountering the same dialect spoken by distant languages. Second, the script as emergent computation. Here, the universe is less like a pre-written play and more like a system that computes outcomes. Local interactions lead to patterns that are not reducible to a single law, but instead are the result of many iterations of feedback and selection. Complexity arises when simple rules interact across scales. Under this interpretation, authorship is distributed. There is no single author but many local processes that act like scribes, each writing marginalia that later coalesce into text. Evidence of such a script would be messy, fractal, and context-dependent. Fossil records would display convergent solutions, technologies might spontaneously reappear in separate lineages, and traces of past complexity might be embedded in patterns that only make sense when interpreted through the lens of dynamics and self-organization. Third, the script as intentional design, an imprint left by intelligence, perhaps by beings contemporaneous with or prior to humanity, perhaps by non-biological actors. This possibility is the most alluring and the most dangerous for the imagination because it offers an author who can be addressed. An intentional script might be composed to last. Its creators might have engineered durable signatures into planetary materials, or they might have seeded messages into astronomical phenomena, but intentionality does not guarantee legibility. Deliberate signals can decay, be misinterpreted, or be too sophisticated for later interpreters. Moreover, a message etched deep into basalt or encoded in the isotopic composition of noble gases might read as noise to an observer without the right key. The archaeological record of an intelligent author's hand might, paradoxically, be indistinguishable from the background hum of a self-organizing world. Across these possibilities runs a single, insistent question: what counts as a signature? In searching for an author, the observer must decide which anomalies are meaningful and which are mere flukes. This is not a purely technical decision. It is philosophical. It asks what kinds of explanations are permissible under constraints of parsimony and evidence. It confronts the human tendency to see patterns when none exist and, conversely, to dismiss subtleness in favor of the dramatic. To navigate this tension, a methodological humility is required. The mind that seeks to read the cosmic script must be willing to tolerate ambiguity, to entertain multiple hypotheses simultaneously, and to value negative evidence as much as positive. Negative evidence, the smoothness of a layer, the absence of a predicted isotope, the lack of technological detritus where it would be expected, can be as informative as a bright speck in a sediment core. A thoughtful observer learns to read silences as part of the text. This is where imagination and restraint must cohabit. Imagination supplies the hypotheses that allow different patterns to be searched for. Restraint prevents wishful interpretation. From converting coincidence into cosmic meaning, the history of science provides salutary lessons. Claims of spectacular finds have sometimes been overturned. In the 18th century, fossils were taken as evidence of biblical floods. In the 19th, the march of uniformitarian geology remade those interpretations. Each corrective was an act of rescribing the story we tell ourselves about the earth. Yet the urge to ask about an author is not merely cognitive. It is an emotional reflex to the pain of contingency and the solace of order. To imagine an author is to imagine that the universe is legible, that there is a purpose to the sequence of events. That sense of legibility can be comforting in the face of mortality and cosmic indifference. It can drive scientific inquiry as much as myth does. Great discoveries have often been driven by a desire to find patterns that make sense of human place and fate. The documentary voice that contemplates these matters must therefore be careful to distinguish between explanation and consolation. There is a kind of beauty in acknowledging that the query about authorship is both a scientific hypothesis and a human yearning. To treat it only as an intellectual puzzle would be to remove its emotional resonance. To treat it only as myth would be to undercut its empirical stakes. The best approach is to hold both threads, the cool rigor of analysis and the warm curiosity of wonder. As the narrator traces these ideas, the cosmos itself is not a static backdrop, but an active participant in the conversation. Planetary surfaces, ice sheets, sediment layers, and planetary atmospheres all function as records and editors. They are the medium through which any script, be it law, emergent, or intentional, becomes legible. They are the palimpsest upon which errors write and then scrape out each other's marks. Understanding that interplay is essential to any investigation into authorship. Finally, the question posed at the outset is also a charge. It asks the listener to join an inquiry that will unfold across many parts, to consider the scale of time that swallows empires, to learn the ways erosion and chemistry dissolve inscriptions, to examine the kinds of signatures that might persist, and to assess the philosophical and methodological frameworks that allow an observer to interpret them. This first section is thus both primer and provocation. It establishes the stakes, smallness, temporality, and mystery. It sets the tone, reflective, precise, and patient. It promises neither answers nor certainties, only a disciplined curiosity. In that space between a stage and a song, the narrator suggests one final thought: whether or not there was an author. The act of asking reconfigures the stage itself. Observers who seek the script alter their questions, their instruments, their conceptions of what is meaningful. They become part of the ongoing performance of the universe, readers whose scrutiny changes the very text they hope to decipher. In this manner, the search for a scriptwriter becomes a narrative that folds back upon itself, a human story written into the larger ledger of deep time. The pause that follows this opening question is not empty. It is full of possibilities. It contains the whisper of eroded letters in ancient rocks, the faint trace of a once unusual isotope, the lingering hint of a pattern no longer obvious. It invites patience and cautious curiosity, because answers, if they come, will not arrive as declarations, but as a slow accumulation of evidence, a sedimentation of small facts and robust arguments. The search will require instruments tuned to the long term, an imagination that respects constraint, and a humility that recognizes how easily cosmic scripts can be rewritten by time. This is the beginning. From here, the inquiry will turn its gaze to the ways deep time hides and reveals, to the signatures that might survive cataclysms, and to the analytic tools that can separate the authored from the accidental. It will probe how the Earth, over eons, plays the part of both stage and censor, and will ask whether, in the silence that follows the last scene, any line of the original script can still be read. What if the stage itself were not a fixed thing? What if the blank expanse that holds the actors and the props, that silent, unquestioned ground called space, were less a passive backdrop and more an active, changing script? The question slips under the skin of every investigation into deep time. It reframes the simplest assumption that events happen in a place that is already there. If the nature of space is uncertain, and the very notion of a record, of something preserved, becomes slippery, the idea is old and stubbornly modern at the same time. For centuries, thinkers argued whether space was a container, an infinite, stable vat into which matter was poured, or merely the set of relations between things. Newton treated space as absolute, a silent theater whose geometry existed independently of its performers. To imagine otherwise would be to imagine actors without a stage, and that thought was dizzying. Leibniz pushed back. Space, he said, was nothing more than the network of relations among objects, distances, directions, and orderings without the need for a separate arena. The divergence between these two images is not merely semantic, it determines how one conceives of permanence. If space is a container, one can imagine inscriptions scratched into its boards that endure. If space is relational, inscriptions are patterns of connection that only make sense as long as the relations hold. In the modern era, Einstein recast the discussion in language neither wholly container nor merely relation. Spacetime, in general relativity, is a fabric that reacts. Mass and energy curve it. Curvature tells matter how to move. Space no longer sits passively. It breathes. Its curvature is part of the dynamical story. The stage flexes under the weight of the drama, folding and stretching with the passage of actors and scenes. That realization opened a new set of anxieties for the imagination. If the stage bends, then a line drawn on the floor might be stretched into a shape no longer recognizable, a script turned into an unreadable smear by the motion of the set itself. Theoretical physics in the 20th and 21st centuries has deepened the estrangement. Quantum mechanics and relativity, when pushed to their joint extremes, suggest that space-time may not be fundamental at all. Instead, it could be an emergent phenomenon, a macroscopic pattern arising from microscopic degrees of freedom that do not look like space in any naive sense. In such a view, space is like a herd behavior that matter and information fall into. It is a collective illusion, robust at large scales but constructed from something else at the bottom. This is not mere speculation for philosophers, but a substantive hypothesis in the sciences of the small and the very large. Physicists have proposed that entanglement, the bizarre quantum link that ties separated particles into a single description, could be the thread that weaves spatial geometry. The idea produces an arresting image. Space is a tapestry woven from entanglement, with each thread an informational bond. Pull enough threads taut, and a continuum appears. Cut them, and the fabric frays. In that construal, adjacency is not primitive. Two regions sit side by side because underlying quantum degrees of freedom are highly entangled. Separation arises when those connections weaken. Space, then, is an emergent map of relationships in the underlying information network. The holographic principle takes the unsettling further step. It proposes that, in certain regimes, the information contained in a volume of space can be encoded on a lower dimensional boundary. A three-dimensional scene becomes, in a precise technical sense, a two-dimensional projection. The realization is counterintuitive and elegant. What looks volumetric might be reducible to information encoded elsewhere. If so, the permanence of records might depend not on the volume where events occurred, but on the stability of some boundary or encoding layer. The stage, in that metaphor, is a projection booth. Destroy the projector, and the play vanishes, even if the actors remain. Other frameworks, causal set theory, loop, quantum gravity, approaches that posit discrete atoms of space. Imagine a universe where the continuum of space-time dissolves into a combinatorial network at the smallest scales. Space, measured by counts of links and nodes, is granular. The continuity that lends itself to long-term records becomes an emergent approximation. Records that depended on the smoothness of the continuum might be vulnerable to discreteness. Seams appear, continuity breaks, and the idea of a slowly eroding inscription becomes confused with a mosaic whose tiles are occasionally rearranged. Each of these scientific visions carries implications for the survival of a script. If space is an active fabric, or an emergent map of information, then the persistence of a message or artifact is not simply a matter of robust materials in isolation from weathering. It becomes a question of the underlying structures that support space itself. An inscription scratched into a rock is meaningful only if the rock's spatial relations to the rest of the world remain recognizable. The rock must still occupy roughly the same neighborhood in the entanglement tapestry. If those relationships are reconfigured by cosmic processes, by phase transitions, topological rearrangements, or the slow decay of entanglement, then the message can be relocated, scrambled, or effectively erased, not by the processes of corrosion and plate tectonics alone, but by shifts in the substrate that defines where and when. This shift in perspective inflects the emotional resonance of deep time inquiry. A feeling that rises a particular kind of fragility, not only of artifacts, but of the notion of location itself. The observer who has spent a life imagining the past as a series of objects placed in a fixed geography must now confront the possibility that the geography is an emergent notation, that the coordinates used to map history are meaningful only when certain informational patterns hold. There is vertigo in this thought. It suggests a radical humility. The cosmos can erase more than content. It can reconfigure the alphabet in which content was written. Yet there is also a certain austere beauty in the idea. If space arises from information, then the universe is in some sense self-documenting. Patterns of entanglement carry a history of interaction. The tapestry of space may therefore contain echoes of process, faint signatures of ancient couplings that persist in the structure of correlations. An ancient event could be read as a statistical anomaly in the web of entanglement. In other words, even if the stage is not a permanent board to be carved on, its weave may preserve memories in its patterning. The question becomes practical: where and how to look for such patterns. A speculative documentary that seeks to trace erased civilizations or the fingerprints of a cosmic author must therefore consider a broader portfolio of potential archives. Stone and ice remain important, but a deeper search might look to the relational substrates themselves. Patterns in the cosmic microwave background, subtle anisotropies in the distribution of galaxies, or unusual correlations in the quantum noise of black hole horizons could be the place where the handwriting of the deep past persists. Gravitational waves, ripples in the fabric of space-time, carry information across cosmic distances with remarkable resilience. They record cataclysms, and their waveforms are not subject to the same forms of local erosion as matter. Space is dynamic. Its vibrations may be the only medium capable of preserving certain truth-like features across eons. Consider, as a thought experiment, the difference between carving a sentence into a cave wall and encoding the same sentence into the entanglement pattern of a region of quantum fields. The cave wall is legible to any agent that still recognizes the language and stands in the same place. The entanglement encoding requires access to the same informational degrees of freedom that composed it, a different kind of access that may be preserved under different physical processes. In some regimes, entanglement can be surprisingly robust. In others, it decoheres with alarming speed. Whether either mode of inscription is more permanent depends on the scale of time and the kinds of upheaval it must survive. The philosophical stakes are high. If space is substantive and abiding, then searchers for signatures can prudently focus on durable matter and local strata. If space is structural and ephemeral, then the conceptual apparatus must expand to include non-local, relational, and informational traces. The two visions demand different instruments and different taxonomies of evidence. They also invite different interpretive habits. The container picture inclines toward material archaeology. The relational picture invites a kind of information archaeology, reconstructing histories from patterns of correlation, from statistical asymmetries, and from anomalies in expected entropic balances. The debate is not merely technical. It shapes the emotional tenor of the search. In one mood, the cosmos is a ledger, and every durable scratch is an appeal to posterity. In another, the cosmos is a living network, and memory is woven into the dynamics of connection. The former comforts with the hope of legible monuments. The latter enthralls with the prospect that history might be hidden in the texture of relationships, waiting for a sufficiently patient and imaginative interpreter to read it. There is also a practical reconciliation. Even if space is emergent, it is emergent in patterns that appear stable at large scales. Human history, after all, was written in a regime where space-time feels continuous and dependable. Geological processes, sedimentation, chemical stratigraphy, these remain reliable recorders. The question is one of scale and exceptional processes. Most of Earth's record will remain well modeled by the container-like intuition for timescales relevant to life and civilization. But for the deepest intervals, for epochs where space-time itself might undergo topological transitions, or where cosmic scale events reconfigure the entanglement web, the emergent nature of space becomes unavoidable. Those are precisely the regimes where erasure is most thorough and the search most challenging. The observer, then, must learn a double literacy. One script is written in rocks and ice, isotopes and tree rings, the tactile, conventional archives of planetary history. The other is written in correlations, in the spectral fingerprints of radiation, in the geometry of space itself. To strike chapters from either book alone is to risk blindness. The speculative documentary approach requires that both forms of evidence be entertained with proper caveats, a clear-eyed account of what each method can and cannot reveal. There is a moral dimension, too. The notion that space might be as much a pattern as a place introduces a humility about authorship. If a cosmic author existed, their choice of medium would be consequential. To ensure posterity, such a creator would have to write in ways that survive not only the weathering of materials, but the possible reconfiguration of the stage. The most assured message would thus be one that leaves traces in the invariant structures of the cosmos, in symmetries, conserved quantities, or statistical irregularities built into fundamental distributions. A designer who understood the emergent nature of space might be expected to deploy redundancy, to encode a message across multiple substrates, geometry, radiation, chemical isotopes, hedging against modes of erasure. For those who prefer the simpler consolation that the stage is a durable board, the thought is perversely optimistic. A consistent stage makes the search for traces more straightforward. It allows hope that an inscription could remain legible long after its authors are gone. For those attracted to the relational picture, the hope is more subtle and perhaps more profound, that the universe's own architecture might conserve a form of memory not tied to matter but to information. The two hopes are not mutually exclusive. They coexist in a dialectic that drives empirical curiosity and philosophical reflection. Ultimately, the question of space's nature reframes the notion of where in the search for deep-time authors. To look for signs of past intelligence or for a cosmic script is to commit to an ontological wager to some working model of space. The consequences of that wager ripple outward, from the choice of instruments to the way anomalies are interpreted. The prudent investigator will hold the wager lightly, testing findings against multiple models of space-time and allowing the data to push the metaphysical assumptions. As the speculative inquiry moves forward, the stakes will become clearer. Subsequent chapters will examine the means by which the planet preserves or erases information, the kinds of anomalies that would constitute evidence, and the methodological frameworks appropriate to a universe that might or might not consider its stage permanent. The present meditation on space is an effort to enlarge the imagination while narrowing the tools of inference. It asks the listener to inhabit both images at once, to envision a theater whose boards can be read and a loom whose weave encodes memory. That dual image of a floor that can be carved and a web that can remember is a productive discomfort. It compels a search that is interdisciplinary by necessity, a search that mixes geology with quantum information, archaeology with cosmology. It teaches a form of patience, that not every answer will arrive as a fossil or a relic. Some answers, if they exist, will be statistical murmurs in the weave of reality. They will demand careful listening and a willingness to translate between grammars. The curiosity that began with the question of an author now turns to a more technical and more human inquiry. What kinds of marks are legible to beings constrained by particular sensory and theoretical apparatus? What does survival mean when the stage itself can alter? In the silence after these questions, the mind that observes is reminded again of scale. The smallness of human time persists as a moral fact in any account, but the vastness of physical possibility demands that humility be matched with ingenuity. The search must be broad and patient, attuned to stones and to correlations, to ice cores and to gravitational murmurs. The nature of space is not a minor philosophical quibble. It is the grammar of the inquiry. To wonder about the universe's author without wondering about the medium in which that author would write is to seek a letter without reading the envelope. And so the investigation continues with a new sensitivity. The narrator, speaking for a collective curiosity, suggests keeping two maps open, one of matter, one of relation. Both may hold the marks of events long gone. Both may be rewritten by processes that outscale human lifetimes. To read the deep past will require a polyglot imagination, one fluent in stratigraphy and in entanglement, in corrosion and in correlation, and a patience that respects how profoundly the notion of where depends on what space itself might be. Could time itself have a beginning? Could the river that seems to carry history have once been frozen into something that was not? Time at all, a stillness of possibility from which moments later erupted, the question slides quietly and inexorably toward the center of any inquiry about origins. It reframes Big Bang not simply as a hot point in the past, but as the place where the very notion of before may lose its meaning. To imagine time's origin is to ask whether there is anything like a pre-temporal realm, a domain not of clocks and sequences, but of relations, amplitudes, and potentials, and whether the small, violent thing we call a beginning is an eruption from that quieter substrate. The Big Bang has, for more than half a century, functioned as both a scaffold for cosmology and a rim beyond which language falters. It is the moment when density and temperature climb to extremes, when the classical equations of general relativity point toward a singularity in the comfortable vocabulary of before and after seems to break down. Science often speaks as if the Big Bang is a starting line, but physicists who press against the equations find a different sensibility. The mathematics that describes space-time dissolves as scales approach the Planck length and the Planck time, unimaginably short. Intervals, roughly 10⁻43 seconds. At that scale, quantum effects are not perturbations on a classical stage. They are the stage. The continuity of time, the steady beat that human beings take for granted, becomes an emergent drum, not an axiom. There is an emotional tenor to this realization. It produces vertigo and consolation in equal measure. Vertigo because the familiar scaffolding, cause and effect marching along a timeline, may be a latecomer, a pattern that organizes itself only after a deep pre-temporal ambiguity resolves. Consolation because the notion of a beginning suggests that the universe might be intelligible as a process that sprang from something simpler, even if that simplicity is of a kind that does not resemble anything in ordinary experience. The mind must stretch to imagine a nothing that is not utter absence but a quantum no-man's land where histories are not yet distinct and probabilities are the primary currency. The theories that confront this territory are diverse, and each attempts, in its own language, to translate what came before into something evocative and testable. One of the older, more striking mathematical voices is the Wheeler-DeWitt equation. In canonical quantum gravity, this equation is sometimes rendered as H0, a formulation that appears to banish time from the fundamental wave function of the universe. There is no explicit time parameter in the equation. Instead, the whole universe is described by a static object whose internal correlations encode what later looks like evolution. This is not to say that change is impossible, but rather that change might be a relational illusion, real in its consequences, but not a fundamental variable in the underlying law. The Hartle-Hawking no-boundary proposal reframes the origin in geometric terms. It replaces a singular, sharp beginning with a smooth rounding off in a sort of Euclidean, time-like geometry. Near the supposed origin, the distinction between time and space blurs, and the universe behaves more like a finite object with no edge than like a line with a starting point. The image is compelling rather than emerging from nothing. The cosmos transitions from a regime where time dimensionally blends into space, making the question before the beginning ill-posed. Lincoln and others have offered complementary pictures, in which quantum tunneling from a state that lacks classical space-time produces a universe. In those accounts, the nothing that begets something is not absolute nothingness, but a quantum vacuum, a seething field of possibilities without temporal order in the classical sense. Loop quantum cosmology paints yet another portrait. In this approach, the discrete structure of space at the Planck scale, a weave of quantized geometry, prevents the formation of a singularity. Instead of a beginning, there is a bounce. A previous contracting phase reaches a minimum volume determined by quantum corrections, then re-expands into the cosmos observed today. Temporality here persists, but its character changes near the bounce. Time does not disappear so much as it is reshaped by quantum geometry. Emotionally, this idea is easier to hold. It allows narratives of antecedents, of cycles and echoes, albeit ones that are written in a language of quanta and discrete transitions rather than smooth classical flows. Across these theoretical landscapes, a common motif recurs: time in its fundamental description. It may not be a background coordinate ticking uniformly. Instead, it could be emergent, a derived notion that arises from the correlations among quantum degrees of freedom. This relational idea has a venerable history. Page and Witters, for instance, argued that time can appear through correlations between parts of a closed quantum system. If one subsystem behaves as a clock, then the correlation of the remainder with that clock defines an effective evolution. The universe as a whole may be described by a timeless wave function, yet observers within it will witness change because they are part of subsystems that correlate and decohere. Time, in this picture, is a perspectival construct produced by entanglement and observation. That notion links to deeper questions about the arrow of time. Why does entropy increase? Why does cause precede effect in the macroscopic world? The most straightforward answer, at least physically, appeals to the universe's initial low entropy state. If the early cosmos began in an extraordinarily ordered condition, then the subsequent thermodynamic unfolding naturally creates an arrow, a relentless march toward greater disorder. But this answer pushes the mystery backward. Why that low entropy beginning? Some proposals import cosmological mechanisms, inflationary dynamics, quantum gravity constraints, special initial boundary conditions to explain the low starting entropy. Others flirt with anthropic reasoning. Perhaps only universes with such initial conditions can support observers who can ask these questions. The emotional weight of this problem is not merely academic. It carries existential overtones. The arrow of time is the skein that ties human memory, causation, history, and responsibility into an intelligible weave. If that skein is contingent, then the humanity that reads old stones and ice cores, that interprets the script of the deep past, is engaged with a fragile structure contingent upon a particular cosmological choice. Conversely, if the arrow is an emergent byproduct of entanglement patterns or a consequence of quantum correlations in the primordial wave function, then memory and history are not absolute banks in the river of being, but locally coherent eddies that permit the illusion, or reality, of persistence. What does this mean practically for the search for traces of deep time authorship? If time is emergent from quantum correlations, then the deepest archives might not be fossils or isotopic anomalies alone. They might be encoded in primordial fluctuations, that inflation stretched into the seeds of galaxies, in subtle patterns in the cosmic microwave background, or in the spectrum of primordial gravitational waves. The initial quantum jitter of fields, the jitter that seeded cosmic structure, is an imprint of processes that operated when classical time was tenuous. Those imprints are not direct recordings of events before the Big Bang, but are consequences of quantum amplitudes that were shaped by physics in regimes where temporality was itself forming. Inflation, if it occurred, also provides an unsettling possibility: the creation of pockets of space-time by quantum fluctuations in a false vacuum, where universes bud off like soap bubbles from a boiling cauldron. The multiverse picture that emerges from eternal inflation suggests that the notion of a singular, definitive beginning may be ill-defined on the largest scales. Each pocket has its own effective temporal coordinate. The emotional texture here is ambivalent. The cosmos could be more fecund than human imagination allows, but such fecundity scatters signatures across a vast ensemble, making specific ancestral traces hard to ascribe. Detectability returns pragmatically to the instruments of empirical inquiry. What signatures could betray a pre-classical influence? Primordial gravitational waves are prime candidates. Those ripples propagate through space-time largely undisturbed by intervening matter and could carry direct information about the universe's earliest moments. Their patterns might encode telltale spectral shapes or polarization modes that betray quantum gravitational effects. Experiments that measure the polarization of the cosmic microwave background. Pulsar timing arrays that probe nanohertz gravitational wave backgrounds. Space-based interferometers. These are the ears tuned to the deep cosmic song. They listen for harmonics that might be echoes of a time before ordinary time. Other potential traces are more subtle: non-Gaussian statistics in the distribution of primordial fluctuations, spectral distortions in the microwave background, the mass distribution of primordial black holes or relic particle species. These are the small marks that could indicate processes in a pre-classical regime. But the further one ventures into speculation, the more interpretive the exercise. A non-standard signature can be read as either evidence of pre-temporal physics or as an exotic realization of a conventional process. The interpretive discipline must therefore be rigorous, cautious, and cognizant of the human appetite for narrative. Philosophically, the possibility that time had an origin opens an ontological fissure. If there exists a realm outside temporal order, a timeless substrate from which time emerges, what is the status of causation there? The ordinary causal vocabulary is a temporal language. Causes precede effects. In a pre-temporal domain, causal talk either dissolves into a more primitive relation, constraint, consistency, amplitude weighting, or becomes a metaphor. That prospect destabilizes deep-seated intuitions about agency and authorship. An author outside time, if such a thing is conceived, would not make things in the way human authors do. They would set a pattern of relations from which histories unfold. The narrative of instruction and rehearsal gives way to a mathematical or informational stipulation, and the human mind must adjust to a different kind of causality, one that is global, atemporal, and expressed through correlations. There is a poetic turn to be made here, because the art of listening to the past is also an act of temporally situated imagination. Human beings read chronologies and feel comfort when the sequence is coherent, causal, and narratively simple. The science of origins, however, often demands that the listener inhabit a plural stance, to accept that the chronicle they cherish is contingent, emergent, and possibly limited. The sensation is smallness, of place, of tenure, of comprehension, but it is also fertile. The possibility that time itself is a latecomer invites humility and ingenuity. It suggests new archives, new instruments, and new kinds of reasoning that combine thermodynamic, quantum, and geometric thinking. If time did start, if there is a boundary beyond which before is meaningless, then the search for an author or for deep. Antecedent civilizations is constrained by a metaphysical wall. There is a finality to a temporal origin. There simply is no earlier history to seek. That could be disheartening, or oddly consoling. The universe would be finite in its narrative span, and everything that must be explained lies within a single causal tapestry. If, on the other hand, the beginning is a bounce or an emergent transition from a timeless or pre-temporal realm, then traces of antecedent conditions might in principle leak through. Certain global features could be relics, and the task becomes one of sifting subtle statistical fingerprints from a cosmic sediment. Either way, the investigation must be patient and pluralistic. It must combine the archaeology of matter, isotopes, sediments, structural fossils, with the cosmology of correlations, background radiation, gravitational waves. the statistics of primordial inhomogeneities. It must appreciate that what counts as an imprint depends on the nature of time itself. If time is a sequence carved into a plank, then reading old scratches is an exercise in classical preservation. If time is a pattern of relational tension, then the signal is woven into correlations, and the act of detection is an act of translation between grammars. In the quiet that follows this speculative map, a human sensibility rises, the desire to keep asking, to refine instruments, to expand theoretical imagination while remaining tethered to empirical accountability. The search for origins is as much an exploration of method as of content. To probe whether time had a beginning is to test the limits of language, mathematics, and measurement. It is to accept that some answers may remain forever probabilistic, expressed as confidence intervals and spectral fits, while others might come as decisive detections that alter our story. The emotional contour of that acceptance is complex. There is grief for certain kinds of absolute knowledge foreclosed by the physics. There is exhilaration in the new kinds of evidence to be sought. There is a continual sense of awe at the scale and subtlety of the questions. Time, whether emergent or primordial, frames all human inquiry. To contemplate its origin is to confront the very conditions of intelligibility. The act of asking and of listening to what the universe allows one to hear changes the listener. It is a modest, tenacious form of authorship, humanity rewriting its place in the ledger by revision of understanding. As the narrative moves on, the implications of a beginning or of timelessness will ripple into other domains. The search for a cosmic author will be reframed by this metaphysics. Authors could be immanent within time, or their signatures might lie in the atemporal scaffolding from which time emerges. The next chapters will press these ideas against geology, against the record of matter, and against the stubborn processes of erosion and entropy. They will ask what kinds of marks can survive when the medium that defines when is itself a derivation, and they will outline with care the kinds of measurements and patterns that could be read as traces of a deeper temporality. For now, the listener is left with the uneasy and generous thought that time may not be a simple flow from an infinite past to an open future, but a creative contingent structure, one whose origin is both the most intimate and the most alien question human beings can pose. What if the cosmos were not only a ledger that erases slowly, page by page, but a living current that could sweep whole chapters out of reach? The image is simple and unsettling. Galaxies are not merely relics held in place by gravity. They are actors in a play whose stage itself is moving in a way that carries them apart. The motion is not a gentle drift, but an accelerating disassembly. For anyone trying to read the universe's deep history, that acceleration is not a background nuisance. It is a principle that rearranges what will ever be known. Part 4. The Expanding Universe and Dark Energy. The discovery that the universe's expansion is speeding up arrived like a revision in the margins of an already ambitious story. In the late 1990s, two independent teams studying distant Type Ia supernovae expected to see the fingerprints of decelerating expansion, signatures of gravity slowing the cosmic flight of matter. Instead, they found the opposite. Those supernovae appeared fainter than anticipated, as if the fabric of space had been stretching faster than the models predicted. The simplest interpretation was radical. An unseen energy pervades space and exerts a repulsive influence on cosmic scales. The name given to this mystery was modest, dark energy, but its implications were enormous. Imagine for a moment the universe as an ocean current. For much of cosmic history, gravity acted like underwater topography, creating eddies and slowdowns where matter clustered. Dark energy is like a broad wind that speeds the current, lifting water from valleys and accelerating the drift of islands. The metaphor is crude but apt. A tiny pressure, uniformly spread through the vacuum of space, changes the dynamical behavior of the largest structures. A quantity measured in energy per cubic meter, so small that in a laboratory it would be trivial, dominates on scales of billions of light years. The universe becomes, in a way, an accelerating flow, and that flow bends the script of cosmic history. Physically, this repulsive effect can be encoded in the cosmological constant, μ, first introduced by Einstein and later reinterpreted as vacuum energy, the ground state energy of quantum fields. In other pictures, dark energy is a dynamic field, slowly evolving through time, often called quintessence. Still other ideas propose that what looks like a new substance is instead a sign that gravity itself behaves differently on the larger scales. Observationally, the universe behaves as if something exerts a negative pressure, driving expansion with increasing velocity. The exact identity of that something remains the central enigma of 21st century cosmology. This accelerating expansion changes the observational horizons of any civilization. Regions of space that today are bound by light, causality, and eventual communication will, over cosmic time, recede beyond visible contact. Galaxies currently within reach of telescopes and radio dishes will redshift into oblivion as their light stretches into infrared and radio and then into wavelengths where detectors are effectively mute. The local group of galaxies may remain gravitationally bound, an island of matter. But beyond that island, the universe becomes an expanding emptiness. The cosmic event horizon, not a geometric singularity but a limit set by the expansion rate, marks the ultimate boundary of what can be known and what can be influenced. There is a profound epistemic consequence to this. The deep-time archaeologist of the future will have fewer pages to read. Signals carrying the fingerprints of early structure formation will be lost or attenuated. The cosmic microwave background, the leftover thermal glow of the Big Bang, will cool and redshift, slipping into frequencies impractical to measure. Large-scale structure will appear more sparse as distant clusters disappear from view. In a de Sitter-like future driven by a true cosmological constant, the observable universe approaches a stable horizon with finite entropy. Information available to any observer becomes bounded. An infinite cosmos may exist, but what is knowable is finite. The weight of that fact is emotional as much as scientific. The acceleration does more than rearrange galaxies, it reconfigures the conditions for remembrance. The slow solvent of geology erases inscriptions over millions and billions of years. Cosmic acceleration erases by cartography, by altering who can ever receive the light that would testify to those inscriptions. The cosmic wind that lifts galaxies also pushes their testimonies beyond reach. Yet the mystery of dark energy itself is a kind of locus for hope and curiosity. It is the most direct sign that the universe's large-scale behavior might have subtleties yet unimagined. If dark energy is not a simple constant, but a field with dynamics, if it changed in the past or will change in the future, then the pace at which the universe isolates its regions could itself be variable. If the field decays or transitions, periods of differing expansion might pepper cosmic history with windows where information can. Cross-distance is otherwise forbidden. If dark energy were to weaken, the event horizons would recede and previously inaccessible regions could again communicate. Conversely, if dark energy strengthens, in the extreme phantom energy scenario, the cosmic scaffolding could tear in a big rip, dismantling bound structures and erasing archives in a violent, finite-time denouement. Even in less apocalyptic variants, the fact that an all-pervading influence steers the cosmic flow shifts the calculus of what. Strategies are robust for leaving a mark that persists into a distant future. Durable matter, stone, metal, deep ice, will still stand against chemical weathering for long stretches. But when neighbors recede forever and the cosmic background cools into silence, the audience capable of reading those marks becomes vanishingly small. To write for deep time in a universe with dark energy may require encoding messages not only into matter, but into features that survive cosmological dilution, conserved particle abundances, imprinted anisotropies in the cosmic microwave background, or, more speculatively, encoded patterns in the dynamics of fields themselves. The authorship that aims to outrun accelerating isolation must heed the global physics of the medium in which it writes. Observationally, the search for the nature of dark energy has become a central program. Supernovae remain one line of evidence. The cosmic microwave background offers constraints on early universe geometry. Baryon. Acoustic oscillations provide a standard ruler across cosmic epochs. Future surveys, mapping the distribution of galaxies with unprecedented precision, and new probes of gravitational lensing can further constrain whether the repulsive influence is constant or evolving. Each piece of data is a careful measure against which hypotheses are tested. The emotional posture required here is one of persistent curiosity, tempered by the acceptance that answers may arrive as statistical surges rather than single clean revelations. And so the universe's accelerating expansion frames a new kind of humility. It is not merely that the past is hard to recover. The future, too, will be a landscape where knowledge itself becomes rarer. The cosmos, in this sense, is not only an archive being consumed by entropy, it is an eddying ocean that can carry entire archives beyond the reach of any future reader. The question of authorship, then, cannot be disentangled from the question of medium. To address the former is simultaneously to confront the latter. Part 5. Holes. If dark energy sketches the broad lines of cosmic dispersion, holes are the punctures. They are the places where the ledger opens into absence, regions that absorb, confine, or otherwise render inaccessible the information that might have testified to former events. The most literal of these are black holes, objects whose gravitational pull grows so intense that they produce an event horizon, a boundary beyond which no classical signal returns. But holes also names the voids between filaments of the cosmic web and the gaps in records created by catastrophes, mixing, or thermalization. Each kind of hole is a distinct mode of forgetting. Black holes are at once the most spectacular and the most conceptually vexing of these modes. They form when matter concentrates beyond a critical threshold, collapsing space into a region where classical geometry ceases to function as usual. The event horizon is not a place of fire, but a causal margin. What falls in is, in classical theory, forever hidden. For deep-time questions, this is an eraser of the practical sort. Material evidence swallowed by a supermassive black hole at a galaxy's center, the detritus of civilizations, stellar debris, even chemical signatures, becomes inaccessible to outside observers. The black hole is eventual Hawking evaporation, a quantum process that returns energy to the cosmos. It takes astronomically long times for massive holes. The process also scrambles and thermalizes. Whether anything of the information that fell in can ever be read in an intelligible form is the subject of the black hole. Information problem, a conundrum that sits at the intersection of quantum theory, gravity, and thermodynamics. The paradox is not merely mathematical, it speaks to the core of what counts as a preserved record. If a black hole destroys informational correlations by converting structured material into featureless thermal radiation, then certain kinds of histories are lost in principle. The work of theoretical physics over recent decades has suggested more subtle conclusions. Holographic ideas and developments from string theory hint that information may not be irretrievably lost. Rather, it might be encoded in subtle correlations of the outgoing radiation or stored at the horizon in ways that defy naive interpretation. Add CCFT duality, for example, establishes that in certain spacetimes a lower dimensional boundary theory can encode the physics of a higher dimensional volume, a radical proposal that reframes horizons as possible repositories of information. These advances do not yet provide a clear operational scheme for reading ancient messages once they have been consumed by a black hole, but they alter the bleakness of the classical picture. Holes may be less absolute erasers and more inscrutable vaults. Even so, the practical effect remains sobering. Mass concentrations around which life might have coalesced are also zones where records can be lost. Galactic centers are turbulent, bathed in high-energy radiation and punctuated by mergers. Collisions between galaxies drive gas inward, feeding central black holes and converting structured environments into chaotic environments where chemical identifiers are mixed and thermalized. The spatial preference of life for certain regions can therefore align with the universe's most efficient mechanisms for burying its traces. The other kind of holes, cosmic voids, are less dramatic but equally consequential. The large-scale structure of the universe resembles a sponge, dense filaments and nodes threaded with galaxies, interleaved with vast, underdense regions. As dark energy accelerates expansion, these voids inflate, matter flows out of the low-density basins into denser nodes, and the emptiness grows. For the cosmic archivist, the presence of voids is a geometrical form of erasure. Interactions between distant regions become rarer, collisions and transfers of material are deferred, and the processes that might carry signatures across space are suppressed. The cosmic web thus develops not only structure, but also lacunae where nothing much ever happened, or where the things that did happen are stranded and insulated. Beyond the astrophysical sense of holes, there are epistemic holes in the record, unconformities and sedimentary sequences, layers erased by uplift and erosion, isotopic anomalies obliterated by metamorphism. Geological processes create discontinuities that, on human timescales, look like missing chapters. These holes are often caused by ordinary planetary activity, seas rising and falling, mountains rising, glaciers scouring landscapes. For anyone trying to reconstruct a civilization that left only ephemeral fingerprints, such geological lacunae are formidable. They make plausible pasts indistinguishable from fantasy. The absence of a monument is not evidence that the monument never existed. It might have been recycled into new rock. There is a conceptual kinship across all these modes of forgetting. Whether one speaks of event horizons, expanding voids, or unconformities in rock, the underlying processes share a feature. They either remove causal contact or destroy correlations. Preservation of history, after all, relies on correlations between past events and present observables, chemical gradients, spatial arrangements, energetic imbalances. Holes either sever causal chains so that no observer can access those correlations, or they scramble correlations into high entropy states where the original pattern is statistically indistinguishable from background. In thermodynamic terms, holes accelerate the approach to equilibrium or impose causal limits that render equilibrium the only available description. This understanding reframes the search for ancient authorship. It pushes attention toward those traces less vulnerable to the violent reconstructions that holes enact. Conserved charges and global invariance, elemental abundances, isotopic ratios of noble gases, anomalies in stellar population statistics may be more durable than surface inscriptions. Gravitational waves carry information through space-time with unusual resilience. Their patterns are not easily thermalized by local processes and can traverse regions that would otherwise be opaque. In the same spirit, subtle statistical anomalies in the cosmic microwave background or in the microstructure of cosmic fields might preserve echoes of processes that no local archive could. In short, the most promising signatures are those that either protect correlations from scrambling or encode information non-locally so that the act of swallowing or expanding cannot trivially erase them. Holes also prompt a philosophical reflection about limits. Even if information in principle survives, encoded in Hawking radiation correlations, for example, the practical question of detectability remains. The timescales involved can span orders of magnitude far beyond the lifetimes of species, stars, or even galaxies. The universe can be generous with subtlety, but stingy with accessibility. The interplay of dark energy and holes creates a double jeopardy. Expansion isolates, holes hide or thermalize, and time dilutes the urgency of searchers. The result is an existential modesty. The cosmos may conserve more of its history than classical intuition indicates, but retrieving those records may demand instruments, lifetimes, and perspectives that are difficult to imagine. Yet in the bleakness there is an intellectual exhilaration. The very phenomena that obscure also illuminate the kinds of questions that are meaningful. The presence of black holes in cosmic horizons forces rigorous thinking about information, about what it means to know, and about how physical law translates irreversibly into observational consequence. The expanding universe challenges assumptions about permanence and compels a broader conception of archives that includes field, correlations, conserved quantities, and gravitational imprints. In the end, the twin motifs of expansion and holes render the universe a subtler archive than a naive ledger. It is not that the cosmos refuses to tell its story, rather it tells the story in media that vary by scale and resistance. Some narratives survive in stone and ice, and in the stubborn chemistry of isotopes. Others survive as patterns in the geometry of space, as spectral shapes in relic radiation, or as correlations woven into the entanglement of quantum fields. The task of reading that story requires an array of literacies, geological patience, astrophysical breadth, and an information-theoretic imagination that can translate between modes of preservation. The gravity of those requirements is a kind of ethical reminder. Humility before scale, rigor in inference, and inventiveness in measurement are the virtues of any inquirer who hopes to trace the universe's memoirs. Dark energy and holes do not so much close the book as change the language in which the book is written. To continue the search is to learn new dialects, listening for gravitational murmurs as well as for etched lines, attuned to the slow winds that lift galaxies and to the absences that mark the floorboards. The narrative persists, but the reader must broaden their sensibility to follow it. What if the place that keeps the universe's ledger is also the place where time begins to come apart? Near a black hole's event horizon, clocks disagree in a way that reads like a philosophical riddle. To a distant observer, an object falling toward the horizon appears to slow, its motion stretched into an eternal approach. Light from that object reddens and fades until it seems to hang, effectively frozen in the last moments before crossing. Yet for the traveler closing that final distance, nothing dramatic is felt at the horizon itself, no sudden rupture of experience, no visible sign that histories are being rewritten. Two accounts of the same episode coexist, each internally consistent, each telling a different story about when and how things happened. That multiplicity is not merely an observational quirk, it is a crack in the simple assumption that there is a single, universal now. Near these gravitational abysses, time becomes local, perspectival, and strangely fragile. This observation is an invitation. It asks whether the fracture of temporal experience near black holes might point to a deeper, Lesson about the nature of time itself. Does the horizon simply produce a kinematic illusion, an optical trick of general relativity? Or does it reveal structural facts that the continuity of time is contingent on causal connectedness? That the flow humans intuit is an emergent accompaniment to the ability to exchange information? And most provocatively, could black holes, in their paradoxical hunger, hide the key to understanding how time is stitched together at the smallest scales? To follow this thread is to move between precision and wonder. The physics is exact. Equations describe how mass and energy curve space-time, how redshift scales with proximity to compact masses, and yet the interpretations are philosophical. The event horizon is a causal boundary, a surface past which signals cannot return to external observers. It is defined in terms of what can be known, not in terms of local sensations. That definition ties temporality to information. If time's arrow and temporal contiguity are grounded in causal and informational flow, then horizons are where time's usual grammar begins to fray. The first, most immediate lesson from black holes is operational. General relativity tells any distant observer that in falling clocks, slow as they near a horizon, photons climbing out of the gravitational well lose energy, their wavelengths stretch. The external observer sees light delayed and reddened, a message arriving in slow motion before thinning into silence. The infaller, however, experiences a finite, proper time to crossing. Professional precision aside, the poetic consequence is haunting. A black hole can make different observers live different histories. A message that, for one vantage, never quite arrives, is for another as immediate as a blink. The asymmetry forces a recognition that the universe's account of what happened is contingent on where the ledger is read. This contiguity of reading prompts a second, deeper consideration, the relationship between horizons, entropy, and the bookkeeping of the cosmos. In the 1970s, theoretical physics revealed an astonishing connection. The area of a black hole's event horizon behaves like entropy. Bekenstein, and subsequently Hawking, showed that black holes are thermodynamic objects. They have temperature and radiate, and their entropy scales with the horizon area in Planck units. Entropy, in turn, governs the direction of time. The arrow of time in thermodynamics is the arrow along which total entropy increases. If horizons store entropy in their areas, if they are repositories of the universe's ignorance, then they are deeply implicated in temporal asymmetry. A black hole does not merely hide matter, it appears to aggregate ignorance about microstates in a manner that changes the bookkeeping of time itself. That picture leads into the information paradox, a paradox that is less a single problem than a locus where gravity, quantum mechanics, and thermodynamics collide. If matter with structured information falls into a black hole, and the black hole eventually evaporates via Hawking radiation, a thermal flux, where did the information go? If the outgoing radiation is purely thermal, it cannot carry the detailed correlations that once characterized the infalling system. That loss would violate quantum mechanics' unitarity, an outrage to the rules that govern microscopic evolution. Over decades, the paradox inspired heated debate and ingenious ideas. Some proposals suggested that information is lost and quantum mechanics must be modified. Others held that information is somehow preserved, hidden in subtle correlations of the radiation or encoded in degrees of freedom at the horizon. Recent theoretical progress reframed the paradox in sophisticated terms. It is not only about whether information is preserved, but about how space-time and entanglement conspire to make preservation legible. Calculations employing quantum extremal surfaces and the so-called island formula hint that the page curve, the expected time dependence of entanglement entropy for an evaporating black hole, can be reproduced within a unitary quantum theory. In resulting pictures, as a black hole radiates, the entanglement between the radiation and the remaining hole grows and then decreases, suggesting that at some point the outgoing radiation begins to carry the correlations that encode the early information. This is not a simple tossback of a physical object. It is a dramatic reallocation of correlations, a quantum bookkeeping in which entanglement, not matter, carries memory. The image is of information migrating from local degrees of freedom inside the horizon to non-local correlations in the exterior. Radiation, a transfer that redefines what counts as a surviving record. If that mathematical arc holds, the philosophical reading is capacious. Black holes would not be absolute erasers, they would be sophisticated scramblers. They would take structured inputs, mix them into thermal-looking outputs, but preserve coherence and correlations distributed across a larger arena. Time's fracture near the horizon would then be not an annihilation of history, but a redrawing of how history is encoded. The ledger remains, but the ink is spread into patterns that require new interpretive tools to read. Yet this hopeful stance carries practical caveats. Even if information survives in principle, encoded non-locally across Hawking quanta, the timescales and energies involved are formidable. The temperatures of astrophysical black holes are minuscule. Hawking evaporation for stellar mass or supermassive holes takes far longer than the current age of the universe. The technical challenge of decoding subtle correlations in a faint thermal background is not merely engineering, it is a question of feasibility for any species limited by finite lifetimes and resources. The universe might be generous with subtlety and stingy with accessibility. Beyond the information accounting, black holes suggest a metaphysical flexibility in time's nature. Classical singularities, the central regions where curvature diverges, are signs that general relativity, taken to its extreme, loses predictive power. Many speculative theories of quantum gravity propose resolutions. Singularities may be smoothed into exotic quantum states, into bounces that spawn new regions of space-time, or into topological transitions that alter causal structure. In these pictures, the black hole interior is not a mere cul-de-sac of history, but a crucible where the very variables that define time are reconfigured. If true, what falls into a hole could seed alternate temporalities, baby universes with their own clocks, or quantum branches out of which distinct histories emerge. The consequence is dizzying. The black hole's interior could be less an endpoint than a junction in a larger manifold of possible times. Linked to that is the speculative but increasingly discussed ER-EPR proposal, which conjectures a deep identification between geometric wormholes, Einstein-Rosen bridges, and quantum entanglement. Einstein-Podolsky-Rosen correlations. If entangled systems are connected by microscopic wormholes, then entanglement is geometry. The upshot is profound for time. The geometry of space-time, its connectivity, might be built from the web of quantum correlations. Horizons and their entropic areas would then be the physical manifestation of missing links in that web. To alter entanglement is to stitch or unpick geometry. Time, being bound to geometry, would be shaped by the patterns of entanglement. Black holes, as the universe's most intense entanglers, would be crucial in this construction. They would be the workshops where space and time are woven and unwoven. Such conceptions elevate black holes from erasers to editors. They become places where the medium of history, space-time itself, is malleable. That casts the earlier question in new light. If one seeks the deepest understanding of time, where better to listen than to the phenomena that most radically reconfigure causality and correlation? The answer is not a technical shortcut. It is an invitation to a different kind of inquiry, one that combines the observational with the conceptual, the imaging power of telescopes with the algebraic sophistication of quantum theory. There are also accessible empirical avenues, imaging horizons. The Event Horizon Telescope's silhouette of M87, the growing images of Sagittarius A, grants a new intimacy with the near-horizon region. Gravitational wave observatories hear the last music of mergers, the chirps and ring-downs that encode geometries of space-time. Subtle anomalies in these signals, echoes, or deviations from classical templates, would signal new physics at the horizon. If horizons encode and release information in unexpected ways, those deviations may be the clearest hints. The observational program is modest in method but ambitious in implication. Listen carefully to the symphony of space-time. The score may contain lines about how time's notes were first arranged. The narrative arc carries a human tonal register or leavened by sobriety. Black holes do not promise easy answers. They pose constraints on detectability and remind humans of their temporal smallness. Yet they also provide possibly the purest laboratories for probing the foundations of temporality. What survives a fall into a hole? What does it mean for two observers to tell different stories about the same event? How does information migrate when ordinary causal channels close? These are not merely technical puzzles for specialists. They are questions about the conditions that make any narrative, cosmic or terrestrial, possible. Finally, there is a psychological afterword. The image of time fractured at the edge of a black hole resonates because it reflects a common human experience, the sense that memories can be simultaneously vivid and inaccessible, that the past might be preserved in ways that defy straightforward retrieval. In the cosmic analog, black holes embody that paradox on a grand scale. They are repositories of forgetting and potential conservers of correlation. They warn that the universe's memory is not merely a ledger of indelible marks, it is a dynamic system. a distributed archive whose protocols of retention and erasure are governed by the interplay of gravity, quantum physics, and information. To conclude this chapter is not to resolve the riddle, but to sharpen it. Blackness, the literal darkness of horizons and the metaphorical opacity of causal limits, reframes deep time. It teaches that preservation is not only a function of durable matter, but of the connectivity that allows signals to be shared, compared, and recorded. It suggests that the key to time's deeper nature may lie where space-time bends most severely, where entanglement is most intense, and where thermodynamic bookkeeping reaches its most extreme expression. Whether black holes ultimately prove to be final erasers, cryptic vaults, or the loom of time itself remains an open question. The pursuit of that answer requires the synthesis of observation, quantum insight, and an imaginative humility, the recognition that the universe's most intimate secrets often hide where ordinary intuitions about when and where come apart. Why does time march in a single direction from past into future when the deepest equations that describe matter and light seldom care whether a film is run forward or backward? The question sits at the heart of any narrative about deep time, because it asks not only how things change, but why change has a handedness at all. It is the small, stubborn mystery behind every memory, every fossil, every ruined city. Why are causes behind and effects ahead? Why does entropy, the universal accounting of disorder, seem to insist that the ledger be balanced asymmetrically? The first part of the answer is almost disappointingly ordinary. In laboratories and kitchen sinks, in the slow dissolution of inscriptions, and in the warming of a cup of tea. The second law of thermodynamics announces itself with uncanny consistency. In an isolated system, entropy tends to increase. Heat diffuses from warm to cold, not the other way round. Broken eggs do not spontaneously leap back into bowls. These patterns are not mystical, they are statistical. At the microscopic level, atoms and molecules obey laws that, to a very good approximation, are time reversal symmetric. Reverse the velocities of every particle and the equations still hold. The paradox is that an underlying symmetry yields an emergent asymmetry. That tension is the place where physics and meaning meet. Part of the story is laid out in the quiet work of Ludwig Boltzmann. He reframed entropy not as a moral pronouncement, but as a count. It is a measure of how many microscopic configurations correspond to a macroscopic state. A tidy, low-entropy configuration, a perfect crystal, a uniformly distributed gas at low pressure, corresponds to comparatively few microstates. A messy, high-entropy configuration, a room full of jumbled molecules, corresponds to astronomically many. From this vantage, the second law is simply the overwhelmingly probable tendency of a system to move from special, rare configurations to vastly more numerous ones. Run a simulation of billiard balls 1,000,000 times and the crowd will overwhelmingly see the balls scatter, not reconverge. Yet Boltzmann's statistical reading raises a pressing conceptual challenge if microphysics does not prefer direction. What sets the initial condition that allows entropy to increase? This is the core of Loschmidt's paradox. Joseph Loschmidt pointed out that if the microscopic dynamics are reversible, then so too are their trajectories. Take any history in which entropy climbs. Inverting all velocities would produce a history in which entropy decreases. Why, then, does the universe not simply explore both directions equally? The decisive ingredient is not the dynamic law, but the boundary condition. The universe began, so far as observable inquiry can say, in an extraordinarily low entropy state. The cosmic microwave background reveals a past that was astonishingly smooth and uniform. That homogeneity, paradoxically, is an ordered state. The distribution of matter was far from clumped. Entropy, when gravity is considered, was unusually small. That specialness of the early state is what privileges one temporal direction. Given the overwhelmingly larger number of microstates corresponding to later, more inhomogeneous configurations, the probabilistic flow is toward increasing gravitational clumping, star formation, and, ultimately, the growth of entropy. The emotional core of this physical point is instructive. The arrow of time is not a law in the same direct way that Newton's second law is. It is the consequence of a cosmological condition. To ask why entropy increases is partly to ask why the universe began so special. And that question returns the inquiry to the cosmology discussed earlier. If the Big Bang was not a singular moment but a transition from some deeper domain, what set the initial low entropy? The philosophical unease that follows is natural. The explanation now shifts one step backward. We can explain the asymmetry of time by citing an asymmetric initial condition, but we are still left asking why that condition held. Different lines of thinking attempt answers of varying ambition. Some physicists accept an initial condition prescription, occasionally labeled the past hypothesis, as an additional law-like assumption. It declares that the universe began in an extraordinarily low entropy state, and from that postulate, the temporal asymmetry can be derived statistically. Others seek mechanisms in cosmology and quantum gravity that would make such a low entropy start natural inflationary models, quantum bounce scenarios, or special constraints in the pre-classical regime. Each takes on the burden of producing a special beginning from dynamics that otherwise do not prefer one. Gravity complicates the picture in a way that often surprises intuitions formed with everyday gases. For thermal systems like a room or a gas in a box, homogeneity is high entropy. For gravity, smoothness is low entropy. The early universe's uniformity meant that matter was spread out rather than gathered in dense knots. It had enormous potential to form structure. As overdensities grew under gravity, stars ignited and black holes formed, processes that massively increase entropy. Black holes, in particular, are titans of entropy. A solitary supermassive black hole can possess an entropy larger than that of many galaxies combined. The path from smoothness to clumpiness is a route to vastly larger entropy, and that route aligns with the thermodynamic arrow we experience. This interplay between gravitational and ordinary thermodynamic entropy has direct bearing on the question of legible records. Memory, in brains or in rocks, is about carving correlations, setting a neighborhood of particles into microstates that reflect a past event. The creation of a record locally decreases entropy by establishing ordered relationships, but doing so always requires expenditure of free energy, which increases entropy elsewhere. Over cosmic time, the net flow is toward higher total entropy. The fragility of records is the dark twin of this process. The same inexorable broadening of microstate possibilities erases fine-grained correlations, turning inscriptions into statistical indistinguishability. Quantum mechanics adds a further layer. Decoherence, the interaction between a system and its environment, explains how quantum superpositions become effectively classical mixtures. It is an entropy-increasing process. Information that could in principle specify coherent quantum phases disperses into many. Environmental degrees of freedom becoming practically unrecoverable. Decoherence bridges the microscopic symmetry and macroscopic asymmetry. It converts potential time-symmetric amplitudes into effective classical outcomes whose histories align with a temporal arrow. But even decoherence depends on initial conditions and on coarse graining choices. Which degrees of freedom are treated as the environment? How coarse are the macroscopic variables? The answers, again, encoded dependence on context and on the past hypothesis. A persuasive way to approach the mystery is to think in terms of typicality and probability. Given a particular low entropy start, almost all microscopic trajectories lead to higher entropy in both temporal directions away from that start. But humans and all other observers find themselves in a branch where entropy increases to the future. The asymmetry is therefore a product of living in a region of space-time where the past was special. It also brings forward awkward but unavoidable anthropic considerations. If the universe were a gigantic thermal equilibrium without special initial conditions, then local fluctuations could, with fantastically low probability, produce temporary pockets of low entropy, Boltzmann brains, in which an observer perceives a consistent past that is illusory. The ubiquity of the past hypothesis avoids the dominance of such weird instances by specifying a universal initial resource of low entropy across which ordinary histories like ours are typical in a way that transcends ephemeral fluctuations. Everywhere in this narrative, entropy is a form of accounting for possibilities, but the meaning of that accounting is nuanced. Entropy can be framed as disorder, as missing information, or as the logarithm of microstate counts. Each metaphor has edges. Disorder captures a felt sense. Missing information aligns with information, theoretic formalism. But the anthropic and statistical core, which microstates are probable and how rare initial states lead to observed arrows, is the axis on which explanatory weight spins. There are practical corollaries to this conceptual edifice. If the arrow of time is a global, cosmological feature grounded in the universe's initial conditions, then local reversals are effectively impossible beyond toy experiments. Macroscopic violations, a shattered cup reassembling, would require an astronomical improbability. If, moreover, the initial low entropy condition is tied to the universe's early smoothness, then searches for prior civilizations or deep time authorship must reckon with the same constraints that scope the arrow. Records are local, fragile islands of low entropy maintained at cost. Global legibility is rarer the deeper one looks. Entropy also points toward the universe's future. In many cosmological scenarios with continual expansion and persistent dark energy, heat, death, a state of maximal entropy, where no free energy remains to sustain processes that create and maintain structure, is the asymptotic fate. Memory fades in such futures not because matter dissolves, but because gradients disappear. The ability to write new low-entropy configurations vanishes. From the perspective of a speculative archaeologist, the implication is stark the farther one peers forward. The smaller the set of potential readers and the less dramatic the contrast that can preserve a script, the combined action of entropy and accelerating expansion isolates and homogenizes the future observational arena, compressing the types of legible signatures that can outlive eons. Yet entropy is not merely an enemy of memory, it is also the engine of history. Without the gradient from low to high entropy, there would be no asymmetric flow to power processes, arrange structure, and allow the evolution of complexity. Stars shine because gravitational collapse transforms potential into heat. Planets sustain. Chemistry, because gradients provide a surface for engines that exploit free energy. Minds remember because they create and sustain local reductions of entropy. The same statistical tendency that erases also permits the long intervals during which information can be written, compared, and sequenced. It is an inversion that merits reflection. The arrow of time both enables and ultimately limits the narrative of the cosmos. The story is not closed. There remain deep, open questions that sit at the interface of physics and philosophy. What exactly determined the low entropy initial state? Is the past hypothesis a brute fact? Or is it derivable from deeper quantum gravitational laws? Could there be cosmological histories in which entropy decreases into the future, seeded by boundary conditions at both temporal ends? How do measures over possible universes affect typicality arguments? And what role might quantum cosmology play in selecting histories that permit observers? For the inquirer of deep time, these puzzles are more than abstractions. They determine what kinds of evidence are likely to survive, how narratives can be stitched together, and what it even means to say that the universe has a history. The arrow of time is the thread that ties together the harmony of cause and effect, the accumulation of records, and the inevitability of forgetting. In a practical sense, it sets the permissions and limits of any speculative search for ancient authorship. Records must be both durable and accessible within a universe whose thermodynamic bookkeeping moves inexorably toward a larger phase space. There is a final, almost moral resonance to the problem. Human beings are beings who remember and who act on the basis of remembered cause. That capacity is rooted in the same statistical asymmetry that marks the cosmos. To confront the question of why time has a direction is to confront the conditions of intelligibility itself. Accepting that the arrow might be a boundary condition rather than an inviolable law invites humility. It reframes grand questions about cosmological origins, about whether prior civilizations could leave legible marks, about the possibility of retrieving pre-temporal signatures as contingent on physical circumstances that lie outside immediate manipulation. Still, the inquiry is energizing. Entropy offers an analytic lens and an ethical prompt. To preserve knowledge is to fight, locally and temporarily, against the statistical tide whose weight is vast. The human project of science, of archaeology, of the attempt to read the ledger of the cosmos proceeds in that constrained theater. It seeks patterns, builds instruments, refines hypotheses, and measures the improbable with patient methods. The arrow of time does not make the enterprise futile. It makes it finite and therefore precious. As the narrative turns the page, the listener is left with a complex inheritance. Time's direction is not a simple decree embedded in the equations. It is a consequence of initial scarcity and statistical predisposition refracted through the peculiar physics of gravity, sharpened by quantum decoherence and amplified by cosmology. The universe chose a direction not because the micro-laws demanded it, but because the cosmos began in a special state that granted an opportunity, a thermodynamic runway along which complexity could flourish. That choice, whether brute or derivable, sets the conditions for all histories, all records, and all attempts to read what the universe wrote in its first chapters. The next stages of the inquiry will press these insights into contact with earthly detail. They will examine how the thermodynamic arrow shapes geological preservation, how chemical and isotopic signatures survive or fade, and what sorts of anomalies could be survivable, traces of deep time authorship. For now, the lesson is both exacting and humane. Time's arrow is a statistical truth that makes memory possible even as it ensures forgetting. To listen to the past is to accept that the cosmos gave a gift, a local and temporary asymmetry whose stewardship carries both scientific urgency and existential humility. What binds particles that are separated by light years? How can two quanta, ripped apart by cosmic distances, still behave as if they share a single fate? The question arrives like a blade of cold light through the familiar curtain of space, an intimacy that seems to ignore the geometry of the stage. It forces a reconsideration not only of how information travels, but of what counts as place and persistence in the universe where the seams between things may be stitched by invisible threads. Quantum entanglement is the phenomenon that answers this question in the language of modern physics. Two or more particles prepared together can emerge from their birth bound by correlations so exact that measuring one instantly constrains the possible outcomes of measuring the other, no matter how far apart they drift. Measured properties come out in patterns that cannot be explained by the notion that each particle carried a local secret written at creation. Experiments have shown that the universe violates any classical bookkeeping that insists on independent local states. The correlations are stronger than chance, stronger than any local hidden variables could allow. They are, in a precise sense, first articulated by John Bell, non-local. The non-locality is subtle. It does not mean messages traverse space instantly. It does not permit the violation of causality in the usual operational sense. Entanglement cannot be used to send instructions faster than light. Instead, it offers a kind of prearranged consistency, a statistical choreography that manifests only when outcomes from separated stations are compared. That paradoxical mix of intimacy and constraint is why entanglement feels like a philosophical prod. It hints that the universe's most intimate connections are not mediated by the classical notion of distance. Laboratory tests transform this philosophical curiosity into empirical fact. In the late 20th and early 21st centuries, experiments closed loopholes, tightened timing, and extended distances. Entanglement was no longer a trick confined to tiny tables and quiet rooms. Photons were entangled, sent down fiber and through air and measured kilometers apart. Space-based experiments pushed further. Satellites beamed entangled photons across hundreds and later thousands of kilometers. Clever cosmic Bell tests even reached for light emitted by distant quasars to set measurement settings. Ensuring that the choices made in the experiment could not have been correlated with the entangled source by any local causal past. The effect persisted. The correlations held, stubborn and precise, across distances that once would have seemed to guarantee independence. If such correlations are possible over planetary and interplanetary scales, what then of correlations that span light years, or those that were imprinted when the universe was young? That question quickly moves from experimental fact to speculative architecture. Theorists have asked whether entanglement is not merely an exotic feature of microscopic systems, but a foundational thread from which space itself is woven. In provocative frameworks, from holographic dualities to tensor network representations, spatial adjacency arises from patterns of entanglement. Two regions sit side by side because the degrees of freedom that constitute them are entangled. Cut those threads, and the neighboring relation loosens. In such pictures, entanglement is not a property that happens in space. It is the thing of which space is made. The image is unsettling and beautiful. Instead of thinking of the cosmos as a set of localized objects interacting across a background arena, one can imagine a vast network of informational bonds. Geometry, distance, closeness, even the flow of time, become emergent descriptions of how the network's correlations are organized. When entanglement is strong and coherent, a smooth continuum appears. When it weakens, separations and horizons emerge. Wormholes and bridges in space-time can be reinterpreted as dense entanglement links. Black holes, in some accounts, are extreme nodes where entanglement is compacted and scrambled. From this vantage, the old questions, where are the durable records? How does the planet remember? Require translation to the grammar of correlations. That translation opens startling speculative possibilities about preservation. If memory can be encoded not only in matter but in the patterning of entanglement itself, then an archive need not look like a monument or a stratigraphic layer. It could be a pattern of non-local correlations impressed on fields or on the quantum state of large systems. Some structures in physics are known for remarkable robustness precisely because of how information is distributed. Topological orders, for instance, code information non-locally. Small, local perturbations fail to erase the encoded data. Similarly, quantum error, correcting code, spread information across many degrees of freedom so that the loss of a subset does not doom the whole message. In the speculative register, an author concerned with longevity might seek to embed signals in such non-local, redundancy-rich forms, not attempting to carve on stone, but to weave into the substrate where locality is an emergent approximation. Reality, however, is not obliged to permit this cleverness. The environment is relentless. Decoherence, the entanglement of a system with its uncontrolled surroundings, destroys delicate quantum phases by dispersing them into many degrees of freedom, effectively converting quantum superpositions into classical mixtures. On a planet seething with thermal noise, molecules bumping and exchanging energy, fragile entanglement is rapidly washed out. In human-scale environments, quantum coherence is fragile. That is why quantum engineers labor to isolate qubits at ultra-low temperatures and in carefully shielded traps. The everyday world, the domain in which civilizations emerge and inscribe messages, is a hostile place for persistent coherence. But the cosmos is not uniformly hostile. Vast cold reaches, the near vacuum between galaxies, or the long, quiet stretches of deep space can provide conditions where certain kinds of entanglement persist far longer than they would in a bustling atmosphere. Gravitationally quiet, low-entropy regions are, in principle, friendlier to quantum coherence. Moreover, certain global imprints, relic correlations frozen into the cosmic microwave background, or the phases of primordial fields stretched by inflation, may survive as statistical signatures long after local coherence has dissolved. The crucial point is that survival depends not only on isolation, but on the kind of encoding. Local, easily decohered phases are fragile, non-local, topologically protected correlations can, in principle, be far more durable. This leads to a practical tension. If entanglement-based records are possible, how would an observer detect them? A detection would not be akin to reading an inscription with a magnifying glass. It would be a matter of statistical archaeology, searching for correlations between physically separated systems that defy classical explanation. The methods are demanding. They require access to degrees of freedom that are not ordinarily compared, long baselines of measurement, and an interpretive framework that can distinguish true non-local signatures from artifacts of selection or coincidence. Cosmologists already practice a variant of this, the search for non-Gaussian correlations in the cosmic microwave background. Anomalies in polarization patterns or unexpected phase relationships in gravitational wave backgrounds are all exercises in decoding correlation-based memory. There is a cautionary tale here about human proclivities. The mind seeks patterns and narratives. It loves to bind scattered coincidences into coherent tales. The same urge that fuels wonder also predisposes to false attribution. Non-trivial correlations can emerge from mundane processes. Selection effects can masquerade as design, and statistical fluctuations sometimes mimic structure. In the speculative documentary voice, this is a central ethical posture to entertain bold ideas without surrendering methodological rigor. The history of science has examples of elegant speculations later undone by careful measurement. Imagination must be paired with skeptical discipline. The deeper philosophical implication is more erosive. If space and time are not fundamental, if locality and temporality are emergent descriptions of an underlying informational network, then the traditional categories of where and when are provisional. The record of an event is not merely its footprint in matter at a place and time, it is a particular configuration of correlations relative to the rest of the universe. An inscription can vanish from rock and yet leave a subtle echo in the web of entanglement. Conversely, an apparently persistent monument may occupy a trivial corner of the correlation structure and thus be less informative than hoped. The metaphysical shift reframes the search for an author. Instead of scanning strata, civilizations, and artifacts alone, investigators must also learn to ask about global patterns of correlation, conserved quantities, and non-local statistical anomalies. Black holes and horizons complicate and enrich this picture. They are regions where causal connectivity frays and where entanglement is both concentrated and scrambled. The theoretical work on black hole entropy and the information paradox suggests that horizons are intimately tied to entanglement. Bookkeeping. Areas behave like entropies. Radiation encodes correlations in subtle ways. Is the deep past were ever encoded in entanglement networks that cross horizons? Retrieving that information would be subject to the same cryptographic complexity that currently frustrates efforts to decode Hawking radiation. The cosmos admits mechanisms that both conserve and hide information, sometimes in forms that are formally recoverable yet practically inaccessible. Speculation about entanglement as medium also forces a re-evaluation of ethics and stewardship. If human civilizations are capable of writing into the fabric of correlation through massive engineering of quantum states, large-scale manipulation of fields, or the intentional seeding of redundancy across many substrates, then the question of whether to do so becomes not merely technical but moral. What responsibilities attach to altering the correlation structure of environments that might be part of other beings' memory? Conversely, if no such deliberate inscription is feasible, then the search becomes an exercise in humility to listen for what the universe, by its own dynamics, conserves. Practically, the search invites concrete strategies. The observational program should widen to include correlation hunts across scales, carefully quantified, model-driven searches for cross-correlations between distant cosmic regions, high-precision studies of polarization and phase, coherence in relic radiation, targeted analyses of gravitational wave backgrounds for unexpected phase relationships. On planetary levels, experiments could look for anomalous, non-local statistical structures in geochemical distributions or in the isotopic signatures that cannot be explained by local processes alone. None of these is a silver bullet. Each demands extraordinary care in controls, modeling, and statistical inference. At the narrative level, entanglement adds a new modality of wonder and of caution. It suggests that the cosmos might carry memory in patterns that are not intuitively spatial. That past and place could be braided into a more abstract web. The image is both consoling and unnerving. Consoling because the substrate of the universe itself might be more tenacious than stone. Unnerving because what survives may be encoded in ways that defy ordinary perception, requiring new instruments and new conceptual grammars to read. For the inquirer of deep time, this means a double practice: broaden the imagination and sharpen the method. One must imagine records cast not only in sediment and alloy, but in webs of correlation, and then build rigorous, falsifiable tests to seek those webs. It is a project that is simultaneously archaeological and computational, geological and quantum informational. It requires humility toward the universe's mistrust of simple narratives and audacity to ask whether memory might be non-local. The emotional contour of that work is familiar, smallness before scale, curiosity unmoored from certainty, and a persistent readiness to revise belief in the light of data. Entanglement does not promise easy salvation for the question of authorship. It instead reframes the problem. If space and time are emergent, then the persistence of a message depends on the durable patterns in the underlying informational network. The possibility that the cosmos preserves aspects of its history in such patterns is tantalizing. It requires imagination to conceive and discipline to test. There is, finally, a philosophical echo to carry forward. Whether or not non-local signatures of past intelligences exist, the fact that the universe admits correlational connections that outlast naive locality invites a new kind of humility about what it means to know the past. The archive is not only a set of stones and ice cores, it is an architecture of relationships whose grammar we are only beginning to learn. Listening to that architecture with instruments attuned to correlations, with theories that respect both quantum subtlety and statistical rigor, may be one of the truest forms of deep-time humility. The thread of entanglement unsettles the notion of absolute solitude in time and suggests that, woven into the cosmos, there may be patterns that remember even when monuments have crumbled. The next challenge is pragmatic, to design the measurements and conceptual tools capable of telling whether those remembered. Patterns are the signatures of chance, of law, or of intention. Is there a clock that ticks the same everywhere? A cosmic metronome whose heartbeat could be inked into geology, carved into basalt, or broadcast as a universal timestamp? The question is simple and stubborn. It presses on the intuition that history ought to be ordered by a single line of time, a common meter that anyone, anywhere, could use to say unambiguously, "This happened then." Relativity, in its austere beauty, answers with a negation that feels almost humane. Time is local. It is stubbornly personal to each path through space-time. There is no single privileged now written into the cosmos. Yet that negation is also partial. Under the scrutiny of theory and experiment, patterns emerge, practical ways to synchronize, to agree, to measure, and those patterns become the instruments by which memory and authorship can be attempted across the eons. The simplest lesson comes from special relativity. When objects hurtle through space, their internal clocks slow relative to distant observers. The Lorentz factor, the familiar gamma 1 ars curtain 1 v2 ace c2 twin, governs the humility of clocks in motion. As velocity v approaches the speed of light c, measured proper time contracts, this is not a poetic aside, but a measurable fact. Subatomic particles produced in cosmic ray collisions, muons for example, live longer in earthly detectors than they would at rest. Their extended lifetimes are the direct signature of time dilation. Particle accelerators routinely correct for relativistic effects. Their engineers do not quarrel with relativity as an idea, only with its arithmetic. Gravity tells a complementary story. In general relativity, mass and energy curves space-time, and clocks sitting deeper in a gravitational well tick more slowly than clocks further out. The effect is small on human scales, but enormous in principle. The frequency shift of photons climbing out of a potential gravitational redshift was verified experimentally decades ago. Pound and Rebke measured it with gamma rays across a laboratory tower. Satellites with their atomic clocks feel the tug of both speed and gravity simultaneously. The practical demonstration is most familiar in the corrections that make GPS work. The constellation of satellites that enable on-the-fly navigation must have their onboard clocks corrected for both special relativistic time dilation due to their orbital speed and general relativistic dilation due to their altitude above Earth's mass. Without those corrections, position errors would accumulate at a rate of kilometers per day. The presence of such corrections in everyday technology is a blunt, intimate proof. Time is not a universal metronome but a local property of world lines. This localness is more than an experimental footnote, it is a philosophical pivot. In the relativistic world, there is no globally valid simultaneity that small minds can take for granted. Two events judged simultaneous by one inertial frame will not be simultaneous in another. The universe refuses a single shared now. Proper time, the time recorded by a clock traveling along a particular world line, is an invariant. Everyone can agree on the proper time that a particular clock accumulates on its own trip. But the comparison of proper times from different, non-coincident paths is coordinate-dependent. It requires a choice of slicing space-time into moments. That choice is a convention, a bookkeeping device that serves observers but does not correspond to an absolute ticking written into the cosmos. Yet the cosmos offers practical anchors. In cosmology, the Friedman-Lemaitre-Robertson-Walker solution provides a preferred slicing when the universe is, on large scales, homogeneous and isotropic. Observers who are commoving with the Hubble flow, those who see the cosmic expansion as an isotropic stretching, can define a cosmic time, the proper time since the Big Bang measured along the world lines of such observers. The cosmic microwave background, CMB, plays the role of a backdrop for this synchronization. If an observer sees the CMB as anisotropic with a dipole pattern, that anisotropy measures their velocity relative to the CMB rest frame. Subtract that velocity and the resulting frame. The rest frame of the CMB offers a natural, operationally definable cosmic rest. Cosmologists use this facility every day. The redshift of the CMB and the scale factor of the universe give a customary calendar for cosmological events. But here is the caveat that must be heard carefully. The existence of a convenient cosmic time in an almost FRW universe is a property of symmetry. It depends on the large-scale uniformity of the cosmos. It is not a metaphysical mandate that time must be globally synchronous. In a universe with strong inhomogeneities or in regimes where space-time itself undergoes non-trivial topological reconfiguration, there may be no natural global slicing. The commoving clocks that cosmology prefers are a pragmatic choice, not an absolute scalpel cutting reality. Thus, while the CMB offers a practical cosmic rest and thus a practical cosmic clock for much of cosmology, it does not restore the Newtonian dream of an everywhere agreed timestamp etched into an eternal stage. The consequences for the possibility of an absolute cosmic clock are subtle. Strictly speaking, general relativity denies an absolute, frame-independent cosmological clock. There is no tensorial object whose value everywhere tells all observers the same elapsed time. But physics does offer invariant quantities that can be used as durable marks. Proper time accumulated along a world line is invariant for that world line. Scalar curvature invariance, conserved charges, topological features, and discrete legible events, the transitions of phase, the freeze-out of particle species, the imprint of primordial fluctuations on the CMB, are coordinates of permanence in a way. That coordinate time is not, for anyone thinking about leaving a message for deep time, whether a hypothetical designer, an ancient civilization, or a future human polity. The lesson is tactical, in code and invariance. If the goal is to make a timestamp legible to distant, diverse observers, then the most robust strategy is to tie the date to something universally observable and locally invariant. A few practical candidates suggest themselves. First, millisecond pulsars behave like natural cosmic clocks. Their pulses are stable over timescales far longer than human civilizations. Their rhythms can be compared across space. A message reference to the phase of a catalogue of widely separated pulsars would yield a consensus that is frame robust in practice. It does not circumvent relativistic relativity. An observer moving at relativistic speed relative to the set will disagree in principle about elapsed proper time, but it provides a shared reference that many observers can use to translate between frames. Second, spectral lines and isotopic ratios embed physical constants. The hyperfine transition of hydrogen, the 21 centimeter line, is a natural reference frequency that will be recognized by any spectroscopically enabled observer. Changes in that line or in the ratios of certain isotopes can signal the passage of processes in ways that survive millennia. These are not timestamps in an absolute sense. They are anchors to which timestamps can be attached. A message that says, this mark was made when pulsar X had phase Y and the CMB temperature was Z, packages a date in relational terms. It is a protocol for translation, not a decree of universality. Third, the CMB itself is a cosmic clock, but a slow, coarse one. Its temperature cools predictably as the universe expands. A sufficiently advanced observer could, in principle, infer the scale factor and deduce an epoch. Any inscription that ties itself to the CMB temperature is offering a global reading in the moving frame. The fragility here is practical. The CMB cools and fades. In the far future, its signal will be redshifted and diluted into frequencies that are challenging to detect. But for cosmological timescales, it functions as a global yardstick. There is also a more abstract, theoretically elegant choice to encode messages in topological or algebraic invariance of fields, patterns that survive dynamical evolution because they are protected by symmetry or topology. Topological charges, like winding numbers or conserved global charges, are immune to many forms of local perturbation. A civilization that understood the vulnerabilities of local clocks might prefer to inscribe an invariant knot into the universes, patterning, not carved in granite but woven into fields, something that survives even when geometry is reconfigured. This is speculative, and the practicalities of writing and reading such an inscription are daunting. But the conceptual point is salient. Invariance beats coordinate convenience when the medium itself is malleable. The relativistic malleability of time also reconfigures how one interprets apparent contradictions in the archaeological record. One need not resort to speculative scenarios about ancient relativistic travelers to appreciate the conceptual lesson. Different observers can disagree about durations measured between events and thus about claims of precedence. When that disagreement is amplified by high velocities or by deep gravitational wells, the notion of a single terrestrial chronology becomes conditional. For the purposes of earthly deep time, however, these relativistic effects are small. Geological clocks, radioactive decay rates, stratigraphic layering, paleomagnetic reversals are measured in local proper time and are robust for inhabitants of the same gravitational potential and modest relative velocities. But if the search for prior intelligences or for messages extends to actors who might have lived in very different frames, aboard relativistic craft or within the centrifuges of deep gravity wells, then the mismatch in proper times becomes a meaningful interpretive problem. It shifts the search toward invariance again. The intellectual pattern that emerges is a double humility. On one hand, relativity removes the comfort of a single cosmic clock, dissolving absolute simultaneity and forcing inquiry into local measurements and relational protocols. On the other, relativity suggests where to anchor hope: in invariance, in conserved quantities, in the CMB and in pulsars, in redundantly encoded non-local patterns that survive the vagaries of motion and gravity. If a message is intended to persist and to be read by diverse observers over eons, its author would be wise to lean on those invariants rather than on a single universal tick. There is an evocative corollary in the overlap between relativity and quantum ideas touched on earlier. If space-time is emergent, a tapestry woven from entanglement or from deeper informational degrees of freedom, then the very notion of a universal clock could itself be an emergent notion. Time's localness would not be a mere operational inconvenience, but a reflection of the way correlations congeal into the appearance of continuity. In such a picture, an absolute time might only exist as a coarse-grained description, a statistical artifact of many entangled degrees of freedom behaving coherently. A would-be author, then, might seek to encode their message at the substratum in entanglement patterns that help form the fabric of space, or in symmetries of fields that persist, even as geometry rearranges. That is the ultimate lesson. To reach across errors when the medium itself can change, one must target what is deeper than the medium. The emotional register of this realization is familiar. There is a smallness in the personal sense. Individuals, civilizations, monuments, all of them are marks on moving clocks. There is a humility that follows. No single perspective possesses the cosmic privilege of an everywhere valid now. Yet there is also an exhilaration in the inventiveness that the constraint invites. Knowing that time is relative does not render the search for authorship hopeless. It refocuses it. It invites ingenuity, encode redundantly, rely on invariance, use global physical phenomena as anchors. It demands patience and a polyglot of measurement, spectroscopy and timing, topological inference and gravitational astronomy. If the question is whether there exists a cosmic metronome whose tick everyone must accept, the technical answer is negative. But if the question is whether practical, intersubjective clocks can be devised, clocks that different observers can use to agree approximately about epochs, then science answers with a variety of strategies. The CMB offers a cosmological timestamp, pulsars, a high-precision beat, atomic transitions and isotopic abundances, a laboratory of standards, and topological invariance, a hope for messages that outlast the geometry of the globe. Each of these is partial. Each requires interpretation and care. Together, they form a toolkit for making history legible across frames. The final, humanly resonant thought is this: relativity teaches that time is not an object to be grasped, but a relation to be negotiated. For those who would write for deep time, whether with stone or with neutrinos, with inscriptions or with pulse patterns, the negotiation is both technical and ethical. It is a promise to understand the constraints of the medium and an act of humility about what will endure. It is also an act of generosity, to encode in forms that allow translation, to build redundancy so multiple readers in different circumstances might reconstruct a shared narrative. In that spirit, the absence of an absolute cosmic clock does not erase the hope of communication across epochs. It sharpens the imagination of how such communication might responsibly be attempted. What if the universe that humanity inhabits were not the whole of reality, but a single room in an immense mansion, one chamber, among countless others, each with its own architecture, light, and clocks? The idea arrives at once as a technical hypothesis and as a vertiginous metaphor. In several scientific and philosophical guises, it asks an unsettling question. Might the familiar flow of time be only a local convenience, a rhythm tied to the peculiar physics of this room, while other rooms keep different hours or none at all? The multiverse and the possibility of additional dimensions begins as a solution to problems of convenience in equations and ends as an invitation to revise basic intuitions about history, causation, and permanence. The mathematical frameworks that lead there are precise. The images they produce are large and strange. In inflationary cosmology, patches of space-time can nucleate and inflate independently, creating bubble universes with different vacuum energies, different particle content, different laws. Inversions of string theory, the fundamental degrees of freedom, allow an enormous landscape of metastable vacua, almost unimaginably many ways to compactify extra dimensions and break symmetries. The Everettian many-worlds interpretation of quantum mechanics multiplies outcomes into branching histories. Each of these ideas implies, in one way or another, that the concept of a single global time might be an impoverished picture. The emotional contour of that possibility is complicated. There is wonder, an expansion of the imagination so vast that the known past seems like a single page torn from an enormous atlas. There is anxiety. If other universes exist, then the search for traces of deep histories becomes not only a matter of decoding a subtle archive, but of understanding that the archive might be segmented by ontological walls. And there is a peculiar humility. No matter how extensive the records on Earth, even an infinitely patient investigator would, by construction, be blind to events beyond certain causal horizons. Physically, The ways that time could differ across universes are varied and precise. A bubble universe that nucleates with a different vacuum energy will have a different expansion history. Its metric, the rule that converts coordinate labels into measured intervals, will differ. Proper time, the time recorded by ideal clocks following specific world lines, is a local quantity. Two observers in different bubbles cannot meaningfully compare proper times except by establishing a physical bridge between them. And that bridge may not exist. In more exotic scenarios, the number of time-like dimensions could differ, some speculative. Mathematical models allow for multiple time directions. Those possibilities are theoretically perilous and empirically remote, but they force a conceptual reckoning. What does it mean for time to be a direction if the dimensionality of temporality itself can vary? A second, subtler point is that different universes might have different thermodynamic arrows. The arrow of time, as described earlier, depends upon the low entropy boundary conditions of a given universe. If one pocket emerges from a vacuum with a high degree of order and another originates from a different condition, their arrows could point the same way, diverge, or be ill-defined by human standards. The idea that in some adjacent domain entropy increases toward what an inhabitant would call their future, while, from that inhabitant's perspective, our direction appears reversed, introduces a metaphysical dissonance. Cross a boundary and a concept of before and after ceases to be a simple label. It becomes a translation problem between. Incompatible thermodynamic bookkeeping, detection is the acid test for any such speculation. Some classes of multiverse are almost tautologically beyond contact, regions so far beyond the cosmological horizon that no light, no gravitational wave, no particle can ever cross. These are level I multiverses in Tegmark's taxonomy, merely more of the same, statistically similar patches beyond the observable horizon. They are astrophysically real yet empirically inaccessible, which is its own kind of sobering fact. Other classes, however, allow the tantalizing possibility of footprints in observable data. Collisions between bubble universes in the course of eternal inflation, if they occurred within our past light cone, could leave circular imprints or anomalous temperature and polarization patterns in the cosmic microwave background. Physicists have proposed statistical searches for such signatures. Analyses using data from WMAP and Planck have looked for the telltale cold or hot disks, for matched circles in the sky, for localized distortions. So far, the results are ambiguous. No definitive collision has been declared, but the search is a model of scientific patience, precise templates, careful accounting for foregrounds, and the sober recognition that a momentary anomaly may be a foreground, a data artifact, or simply noise. There are also gravitational possibilities. A bubble collision is a violent event in the language of space-time. It can generate bursts of gravitational radiation with spectral shapes and angular structure different from those produced by ordinary astrophysical sources. Future gravitational wave observatories with broad frequency coverage, space-based interferometers, pulsar timing arrays, networks of terrestrial detectors pushed to their limits might one day hear the unique ring of such a cosmological encounter. Those signals would not merely say a collision happened, their spectral fingerprints could inform about the energy scales, the wall tensions, and the dynamics of fields during nucleation. In other words, different times and dynamics in other bubbles could leave signatures in our universe's gravitational literature. Yet caution is mandated. The universe is a noisy instrument. Foregrounds, non-linear astrophysical evolution, and instrumental systematics conspire to create false positives. A statistical excess can be enticing. It can also be the mirror in which the observer sees their own hopes reflected. The methodological posture demanded by multiverse science is one of constrained imagination. Generate bold hypotheses, but treat anomalies with the same skeptical rigor that crushed past enthusiasms, from canals on Mars to supposed fossilized footprints. Extraordinary frameworks require extraordinary evidence. Beyond collisions, there are more indirect imprints to consider. If different domains in a multiverse select different values for what in our physics are constants, the electron mass, the fine structure constant, the cosmological constant, then domain walls could traverse regions and imprint shifts in spectral lines. High-precision spectroscopy of distant quasars and stars can measure the fine structure constant across cosmological time. Already, meticulous analyses have set tight bounds on its variation. Yet pockets in space where constant step could, in principle, produce abrupt changes in chemistry and nuclear reactions. The existence of such steps would be a dramatic signal, a local chapter of physics that refused to turn like the rest of the book. The string landscape invites yet another kind of thinking. If vacua differ by the shape and size of compact extra dimensions, then certain massive excitations, so-called collusa, Klein modes, would carry the imprint of those hidden geometries. Colliders, tabletop tests of Newton's law at sub-millimeter scales, and precision cosmological observations together constrain the size and dynamics of extra dimensions. To date, experiments have tightened the net on large extra dimensions, but they have not closed it entirely. The door remains ajar for novel physics, the search for deviation from inverse square gravity, for missing energy events at high-energy colliders, for relic particles that would survive in cosmic backgrounds, is pragmatic archaeology at the frontiers of scale. Philosophically, the presence of multiple universes fractures more than the physical stage. It fractures the notion of authorship. If an agent of intention wished to leave a message that outlasted cosmic weathering, what would be the preferred medium? In a single universe picture, one might favor isotopic anomalies, deep-buried artifacts, or modifications of fundamental constants. In a multiverse, the calculus changes. A designer who understood the multiverse might attempt to write in the language that transcends particular vacua, encode messages and topological invariants of fields in prime number patterns embedded in fundamental distributions or in the combinatorics of cosmological perturbations. Alternatively, a robust strategy might be to scatter redundant signals across many substrates, geometry, radiation, and chemistry, so that partial legibility survives whatever kind of erasure the neighboring metastable states impose. The practical difficulty, and the moral humility it calls for, is that such encodings would likely be subtle and require a shared interpretive protocol that could survive the transformation of when into an incommensurate parameter. The many worlds interpretation raises a different kind of stasis. If quantum branching produces coexisting, non-interacting histories, then there are literally versions of events for every quantum choice. Those branches are not separate universes in the cosmological sense, but are decoherent histories within a single global quantum description. Their multiplicity is profound, but also, for inhabitants of any branch, invisible except as a metaphysical proliferation. The question of time across branches becomes a question of relative histories assembled by decoherence. Every branch carries its own consistent narrative, and no interbranch communication is available in standard quantum mechanics. The epistemic consequence is that the plurality of histories does not help in reconstructing a physically distinct predecessor. Civilization, it only complicates the metaphysical ledger of possibilities. The speculative appeal of multiverses is sometimes balanced by an equally serious epistemic critique, unfalsifiability. If a hypothesis explains every possible observation by placing contradictions in other sectors of an infinite ensemble, then it risks being a way of immunizing theory from empirical defeat. Modern multiverse thinking grapples with this challenge by demanding testable predictions, specific localized signatures, statistical distributions of observables, and the demonstration that certain coincidences become more natural once selection biases are taken into account. The value of multiverse proposals lies not in their metaphysical extravagance, but in their capacity to suggest new empirical programs, to reframe anomalies as potential signals, and to demand rigor in the interpretation of large datasets. For the project of deep time archaeology, the implications are both grim and oddly liberating. Grim, because the very existence of other domains can consign vast swaths of possible histories to inaccessibility. Whole civilizations, entire cosmological narratives could be permanently sealed behind domain walls. The notion of an ultimate, comprehensive paleography of existence collapses into a smaller, more modest ambition: to map what is legible within this causal patch, to characterize the limits imposed by horizons, and to exploit the deepest, most robust forms of imprinting that survive despite cosmological caprice. Liberating, because the multiverse invites investigators to diversify their methods. If stone erodes, look to correlations in the cosmic microwave background and in gravitational waves. If chemistry is vulnerable, search for invariant algebraic structures and global statistical anomalies. The task becomes interdisciplinary in a literal sense. Cosmologists, particle physicists, geochemists, information theorists, and philosophers must coordinate instruments and interpretive protocols. There is also a temporal lesson in the multiverse. Suppose a neighboring bubble ran through its thermal history 1,000 times faster than ours. For observers in that bubble, rise and fall of civilizations could be rapid whirls. For us, they would be brief flashes, perhaps indistinguishable from background transients. Even if signals could cross domain boundaries, and their spectra and durations will be so transformed by the mismatched metrics that recognition would require advanced theoretical translation. The heart of the matter, comparability of epochs across universes, is not guaranteed. To say this happened then, in another bubble, may be as meaningless as pointing to a tune and insisting the same rhythm holds in. A piece written in another meter. Ultimately, the multiverse idea reframes the original question of authorship into a hierarchy of practical and philosophical problems. Which forms of memory are universal enough to survive across vacua? Which observables are invariant under the manifold ways the cosmos can be stitched together? What does it mean to be a reader in a library whose books are written in many incompatible languages? Science can begin to answer these questions by committing to concrete programs. Refined searches for bubble collision imprints in the CMB, targeted gravitational wave spectral hunts, precision spectroscopy to bound domain walls, tabletop tests of extra-dimensional physics, and theoretical work to identify robust invariants that transcend specific compactifications. As with all deep time inquiries, the posture required is a blend of humility and audacity. Humility, because theories may be wrong, because signals are rare and ambiguous, and because the cosmos might be organized in ways that make many of the boldest hopes forever inaccessible. Audacity, because the multiverse, if true, opens a scale of possibility that transforms questions of permanence into new scientific projects, to listen for the faint, non-local murmurs of other rooms, to map the limits of causal contact, to develop the translation protocols that allow epochs in. Dissimilar metrics to be compared. The narrative closes, for now, with an image. The observatory, whether a radio array, a gravitational wave network, a spectrograph, or a precision laboratory, is not merely an instrument, but a lantern in a corridor of doors. Each method illuminates part of the hallway. Each negative result is a shuttered doorway. The multiverse hypothesis suggests that behind some doors there are clocks that keep different time, rooms that archive histories in alien alphabets, and perhaps, behind a rare open passage, a faint trace left by something that once thought to be an author. The search is necessarily partial, methodical, and patient. It is the work of listeners who have learned to translate between scales, to trust statistics without losing curiosity, and to accept that some answers may come as quiet spectral anomalies rather than as loud proclamations. In that acceptance there is a strange comfort, even if other universes keep different hours. The effort to listen across the manifold of possibility is itself a human act of persistence, a small, stubborn attempt to read what the cosmos, in all its multidimensional richness, has been writing. If the deepest equations of physics are machines for generating possible worlds, then some of those machines produce loops, paths through space-time that return upon themselves. The image is arresting, a thread of events curling back until its end meets its beginning, an apparent violation of the simple arrowy march the mind expects. The idea of traveling into the past has lived in myth and fantasy for centuries. In the 20th century, it found a more austere home in mathematical physics. General relativity, Einstein's elegant account of gravity as geometry, admits spacetimes with closed time-like curves. The equation that made possible GPS corrections and black hole imaging also opens, at least on paper, the doorway to histories that fold back on themselves. The tension between mathematical permissibility and physical plausibility defines the drama of this chapter. On the one hand, there are concrete solutions of Einstein's equations, exact geometries that harbor time loops. Kurt Gödel wrote one such solution in 1949, a rotating cosmology where global rotation permits world lines to spiral and return to their own past. Tipler proposed a massive, infinitely long rotating cylinder whose frame dragging could fling causal trajectories around into self-intersection. The spinning Kerr black hole, discovered as an exact solution in the 1960s, conceals regions inside its inner horizon where coordinates behave oddly and, at least in idealized mathematics, closed, time-like curves can exist. These are not rhetorical devices. They are explicit geometries where, in the language of relativity, the distinction between futureward and pastward directions blurs. On the other hand, nature is rarely obliged to respect the freedom of mathematical imagination. The solutions that permit time travel often require conditions that the physical universe seems unwilling to provide. The Tipler cylinder needs infinite length. Gödel's universe conflicts with observation because our cosmos is neither globally rotating nor the same in all directions in the appropriate way. The Kerr inner region, beautiful on paper, is suspect under perturbation. Disturbances may grow without bound near the inner horizon, leading to instabilities or singular behavior that would destroy the neat, looped trajectories. the mathematical allowance becomes, under more realistic conditions, an invitation for chaos. One of the clearest conceptual frameworks for these debates is the wormhole. If space is a tapestry, a wormhole is a stitched shortcut, two mouths joined by a throat, connecting regions that might otherwise be separated by tremendously long distances. Morris and Thorne, in the late 1980s, made wormholes physically respectable in a popular way by showing that a traversable throat could be consistent with Einstein's equations, provided the throat was threaded by exotic matter, energy with negative mass density and negative pressure that violates familiar energy conditions. Negative energy is not purely fictional. Quantum field theory supplies ephemeral examples. The Casimir effect between two conducting plates produces a measurable negative energy density relative to empty space. Yet the scale and control required to keep a macroscopic wormhole door open are orders of magnitude beyond any demonstrated engineering. Even granting a hypothetical traversable wormhole, relativity offers a simple route from space, shortcut to time loop. Suppose two mouths are initially synchronized. If one mouth is accelerated at relativistic speed and brought back, special relativity ensures that less proper time has elapsed for the traveling mouth than for the stationary one. Alternatively, placing one mouth near a massive body where time runs slowly compared to a distant mouth would also create a temporal offset. Once a traveler or a signal steps through the throat from the younger mouth to the older mouth and then returns through the external space-time, the trajectory can close on itself, a loop in which cause and effect juggle chronology. The elegant trick is mundane physics, time dilation, used against itself to manufacture apparent causality, bending. That construction draws attention to the paradoxes that fuel the popular worry, the grandfather paradox, the problem of consistency when an action in the past appears to prevent the agent who performed it from ever acting. If an observer could travel to the past and extinguish their ancestor, how could they exist? These puzzles are not merely narrative car crashes. They illuminate the conflict between local dynamical laws and global consistency. One compelling resolution is the Novikov self-consistency principle. The universe's history must be globally consistent, and any event that seems to create a contradiction is forbidden by the dynamical constraints. In such a world, attempts to alter the past become constrained in subtle ways. Actions that could create paradoxes are suppressed by physical mechanisms or by the only self-consistent outcomes being realized. The price is stark. Free will, in any straightforward libertarian sense, is curtailed within the loop. Quantum theory offers another set of routes through the tangle. David Deutsch proposed a model of quantum closed time-like curves in which quantum states interacting with a time loop evolve into fixed points of a self-consistency map. The result is striking. Paradoxes are avoided because the allowed quantum states are those that remain invariant under the time loop evolution. The Deutsch framework also suggested exotic computational possibilities. Access to CTCs could, in principle, collapse certain complexity classes and allow solutions to otherwise intractable problems. Such findings present a philosophical sharpening. Time loops are not merely metaphysical curiosities. They, if realized, would have profound consequences for information and computation. Yet this same theoretical richness deepens the practical skepticism. For a wormhole-based time machine, quantum effects may be fatal. Stephen Hawking's chronology protection conjecture proposed that quantum fluctuations blow up near chronology horizons, the boundary, where closed time-like curves would first form, producing divergent stress energy that prevents the formation of a usable time machine. Semi-classical calculations suggest that vacuum polarization and particle production around a nascent time loop could deposit enormous energy and destabilize the geometry. Vacuum modes get blue shifted as they orbit within the would-be loop, amplifying until they back-react on space-time. Where classical equations would have allowed a smooth throat and a tidy loop, the full quantum treatment may scatter the ink. The energy conditions invoked earlier play their part. Classical proofs that forbid exotic structures often rely on energy inequalities. Matter that behaves benignly, with non-negative local energy density, prevents certain pathological solutions. Traversable wormholes typically demand violations of the average null energy condition over some region. Quantum field theory does allow localized violations. Negative energy densities can exist transiently, but so far the known quantum inequalities place strict bounds on the magnitude, duration, and spatial extent of such negativity. Ford and Roman showed that the negative energy required to stabilize macroscopic bridges is constrained by quantum inequalities, making the engineering challenge increasingly unlikely. The lesson is one of scale. While quantum tricks whisper of negative energy, Their whisper is too faint and too fleeting to hold open a cosmic doorway of macroscopic size for long. There are still other routes to apparent time travel that evade direct CTCs. Black holes and their hypothetical cousins, white holes, bounce scenarios, and wormhole-like topologies in quantum gravity hint at more subtle reconfigurations of history. Certain models of black hole evaporation suggest that information could re-emerge in radical ways, or that a black hole interior might pinch off into a new region of space-time. If processes exist that spawn baby universes, the causal relationships between parent and child cosmos complicate the simple picture of a single history. Yet these are not time machines that return a message to an earlier epoch of the same universe. Rather, they are branching histories, a way to avoid contradictions by generating new causal tapestries. The thermodynamic arrow of time, the inexorable statistical drift toward higher entropy, casts a long shadow on the whole enterprise. A macroscopic time traveler would seek to reduce local entropy by selecting a low-entropy target window in the past, but the cost of creating such a low-entropy pocket is paid elsewhere and is exponentially unlikely. The past hypothesis that explains why entropy increases in one direction makes macroscopic lowering of entropy a prohibitive statistical miracle without an enormous free energy expenditure. Time travel into a genuinely lower entropy past may therefore not only be dynamically constrained, but statistically suppressed. Asking the universe to provide a crystalline low-entropy slice is asking for an unlikely microstate. Even if the physics permitted travel of information to the past, the practical problem of deliverability, getting a readable, meaningful signal to a past observer with interpretable context, remains daunting. A message encoded in the throat of a tiny quantum wormhole or in a subtle phase relation among primordial modes of a field would require receivers with very particular access to the right degrees of freedom. For archaeologists of deep time, the optimistic thought is that information might leak into the past in ways that leave durable material traces. The pessimistic counter is that any trace must survive the entropic and geological mills, the same slow salvation that erases inscriptions over millions of years. If time travel were to be used as a universal broadcasting strategy, place a warning in the past to prevent a future catastrophe, then its feasibility hinges on three tall requirements: a stable, traversable, causal route, a protocol for encoding robust, interpretable signals, and a receiver capable of decoding in a different epoch and context. Philosophically, the possibility of backward causation unsettles foundational notions of agency and moral responsibility. If actions can propagate to earlier times, the neat, linear accountability that underwrites much of moral discourse becomes muddy. The Novikov principle reassigns the problem into a logic of constraints. The universe's global consistency becomes the arbiter of what actions are possible. An alternative escape hatch uses branching histories. The traveler does not change their originating past, but moves into a different branch whose course diverges. In that, many world-style resolution paradoxes evaporate at the cost of multiplying histories and surrendering the notion of a single shared past. Finally, there is an aesthetic and cultural dimension that cannot be ignored. The human longing to undo mistakes, to witness vanished loved ones, or to intercept ancient disasters is powerful and ancient. Time travel narratives satisfy that yearning in story and myth. But the scientific conversation tempers longing with constraint and invites a different kind of humility, to treat the past as fragile, precious, and stubbornly singular. The machinery of the universe may allow certain non-intuitive causal structures in mathematics, but the full machinery of nature, thermodynamics, quantum field theory, and the pragmatic limits of energy and duration makes physical exploitation implausible. The result is not simply pessimism, it is a subtle reorientation. Rather than dreaming of grand temporal voyages, the inquiry returns to investigative patience, to extract signals from persistent, high-integrity records, to read the entanglement and radiation left impressed by early processes, to use gravitational waves, isotopic anomalies, and invariant signatures as proxies for what cannot be directly revisited. In the end, the question of time travel is less about whether a caffeine jolt fiction could be made real, and more about what the laws of physics truly allow in the reading and writing of history. General relativity opens doors in the equations, quantum theory and thermodynamics close many of them or make their use wildly expensive. If a time loop exists, it is likely to be microscopic, highly constrained, or fundamentally non-utilizable by macroscopic beings. If large-scale backward causation were possible and exploitable, the universe might already show odd signs, paradoxical records, causally inconsistent layers, or anomalies that cannot be reconciled by ordinary inference. The empirical record, across geology and cosmology, gives no inviting evidence of such global contradictions. That absence is itself a kind of data point, one that aligns with several conservative theoretical conjectures. Energy conditions that resist exotic matter at scale, quantum inequalities that limit negative energy, and chronology protection that disfavors exploitable loops. Yet the final account remains conditional. Quantum gravity, the still outstanding marriage of general relativity and quantum mechanics, may change the story in ways one can now confidently anticipate. The topology of space-time, the fate of singularities, and the distribution of entanglement at the Planckian frontier could permit unforeseen channels for causal rearrangement, or they could entrench the universe's reluctance to allow temporal paradox. For those who listen to deep time, this uncertainty is both challenge and invitation. The discipline must combine theoretical daring with empirical humility, testing for subtle imprints that would betray exotic causal events and building measurement programs sensitive to the kinds of non-local correlations that might be the only viable surviving testimony. At the same time, there is an ethical reminder woven through the physics. The past, once gone, seems designed by the laws themselves to resist rewriting. That stubbornness is not cruelty. It is a condition that makes history legible, meaningful, and morally weighty. Time travel, if it is a possibility at all, would not be an easy remedy for regret. It would be a window whose very existence reframes what it means to remember, to be accountable, and to cherish the fragile ledger the cosmos keeps. What if the flow that people feel inside their heads is not simply the echo of the universe's metronome, but a distinct phenomenon, an internal river braided around the external one? And what if that braided pattern is essential to how history is written and read? The idea arrives like a question deliberately aimed not at rocks or radiation, but at the living organ that interprets them. It asks plainly, does consciousness do more than passively register time? Does the mind help fashion the experience of a moment-to-moment sequence, and if so, could that subjective weaving influence what counts as a record in the long ledger of deep time? The simplest observation grounds the inquiry. Human beings do not experience time the way an atomic clock does. A second, measured by cesium oscillations, is the same second for every inertial observer who can agree on the frame. The second A mind lives through is elastic, sticky, sometimes vanishing or stretching like taffy. Minutes in love can condense into instants. A single second of terror can seem to expand until every micro-detail is vivid. Age compresses subjective time. Childhood summers feel endless. Later, decades accelerate. Attention warps duration. Boredom lengthens it. Absorption shrinks it. These everyday distortions are not trivial aesthetic facts. They are the phenomenological traces of underlying mechanisms, neural, metabolic, computational, that orchestrate perception and memory across many scales. The brain keeps time in many ways at once. There are physiological clocks that beat with circadian regularity, governing sleep and hormonal rhythms. There are ultrafast cortical mechanisms that operate at millisecond resolution in the auditory and motor systems. There are intermediate processes that organize working memory and the specious present, the short window in which events are integrated into a perceptual now. Neuroscientists have described distinct substrate for these capacities. The cerebellum and basal ganglia show signatures of subsecond timing crucial for motor coordination. The hippocampus and associated medial temporal lobe circuits contain what some researchers call time cells, whose firing correlates with sequential moments in an experience. Large-scale cortical networks handle the longer time scales of narrative and self-reflection. Those nested clocks accomplish two things essential to temporal experience. First, they bind. The brain integrates multisensory inputs that occur close together into single events. The clap and the flash become a single thunderclap. This binding occurs within temporal windows that vary by sensory modality, which helps explain why the world feels continuous despite its discrete neural substrate. Second, they order. The brain constructs sequences, placing encoded moments into memories and aligning them with expectations about what should come next. Both binding and ordering are forms of compression and categorization. They are the essential cognitive moves that make a stream of physical changes into a coherent narrative. The contemporary theoretical language that ties many of these observations together is predictive processing. In this view, the brain is fundamentally a prediction machine. It continuously generates models of incoming sensory data and updates those models via prediction errors, the mismatches between expectation and input. Time, from this perspective, is the cadence of prediction and correction. Anticipation produces an arrow, futures are hypotheses to be tested, pasts are records of predictions already evaluated. The experience of flow, the felt passage from future to past, is thus bound to the brain's relentless attempt to minimize surprise. This is not merely poetic, it maps onto measurable neural dynamics. When predictions are accurate, processing is efficient, and subjective time can compress. When prediction errors are large, the mind seems to attend more intently, and subjective time often expands as events are scrutinized. Here the link to thermodynamics becomes more than analogy. Prediction error reduction is an informational cost. Maintaining a model, updating it, writing memories, all require work and are embedded within the organism's non-equilibrium metabolism. Memory formation is a local reduction of entropy. Patterns are fixed in synaptic strengths and network states. That local order is achieved only by expending free energy, and the energetic price is paid by the broader environment, increasing entropy elsewhere. Thus, the act of creating subjective continuity, of encoding an I that remembers and expects, participates in the same statistical bookkeeping that underwrites the arrow of time. Consciousness, then, while not overturning the second law, is entangled with it. Subjective temporality depends on the microscopic processes that themselves obey thermodynamic constraints. Philosophy of time offers complementary frames that sharpen the question. The block universe or eternalist picture treats past, present, and future as equally real regions of a four-dimensional space-time. Under that view, the flow of time is an aspect of consciousness, a moving perspective passing through a pre-existing landscape. Contrast that with presentism, which grants ontological privilege to the present alone. Here, the felt present might be metaphysically constitutive. The only real things are those that consciousness encounters now. A third option, the growing block, posits that the past and present are real, but the future is not. Each of these metaphysical positions carries consequences for how the observer's role is understood. If consciousness is the narrator who slices the block into successive nows, then subjective time has a direct, if perspectival, role in the ordering of events. If the block exists independently, the mind's flow is an interpretive phenomenon riding on an already given chronology. Modern physics complicates that tidy separation. Quantum mechanics and the study of decoherence suggest that the appearance of classical histories, the familiar macroscopic sequences, emerges from an underlying web of quantum amplitudes through the process of environmental decoherence. Observers are part of those environments. Some speculative accounts have proposed that measurement and observation, the events by which quantum possibilities become definite outcomes, require conscious agents, or at least agents capable of sustaining robust memory. That suggestion has a long pedigree, from early formulations that treated measurement as conceptually problematic to later provocations by thinkers like Widner. Contemporary debate is more cautious. Decoherence can occur in the absence of conscious agents via interactions with vast environmental degrees of freedom. Yet the special character of memory, the integration of records into a persistent network, remains distinct. Theories such as the global neuronal workspace or integrated information theory attempt to link consciousness to particular modes of information integration. If conscious states are the work of systems that integrate information across timescales and subsystems, then they might also be the loci where quasi-classical histories are stitched into accessible form. This gives rise to a provocative possibility, albeit one that must be held tentatively. The processes that create subjective continuity, the binding of events, the stabilization of memories, the projection of expectations, are precisely the sorts of processes that transform quantum ambiguity into stable classical narratives. They are the local mechanisms by which histories become legible to creatures that remember. That does not mean consciousness conjures global time out of nothing. Rather, it means conscious systems are specialized record keepers. They extract, stabilize, and interpret correlations in the physical world at a pace and in formats suitable to embodied action. From the point of view of a deep-time archivist, this distinction matters. The universe may possess many repositories of correlation, sedimentary strata, isotopic anomalies, gravitational waveforms, entanglement structures, but consciousness translates physical correlation into narrative, linking an event to causes and future consequences in a way that is unique to memory-bearing agents. Empirical science probes this interface with delicate experiments. Laboratory studies of timing and agency reveal that the sense of causation and the feeling of an action belonging to oneself are malleable. Experiments like those inspired by Benjamin Libet's readiness potentials and subsequent replications and critiques have shown that neural signatures of action precede the conscious report of having decided. Other work demonstrates post-dictive reconstruction. A stimulus that arrives after a voluntary action can retroactively alter the subjective timing of the cause-effect pair. Perceptual illusions, temporal binding, chronostasis, the Colify effect show that the brain can rewrite the temporal relations among events to produce coherent narratives. None of these findings proves that consciousness creates objective time. They do show, however, that the ordering and timing that consciousness reports are constructed, convertible, and sometimes at odds with external clocks. The evolutionary logic behind this is straightforward. Organisms benefit from building narratives that compress past events into causal patterns and that forecast future states. A nervous system that selects relevant correlations and hashes them into durable formats for prediction and planning increases in organism survival. Subjective time is therefore not a luxury, it's a utility. Its distortions, time slowing in crisis or time speeding in absorption, are functional adaptations that allocate neurocomputational resources to events worth scrutiny or optimize behavior when precise timing matters. When the scale shifts from seconds and years to geological epochs, consciousness's role diminishes in some respects and intensifies in others. On the one hand, the processes that conserve information on million-year timescales, mineralization, isotopic fractionation, sedimentary layering, are indifferent to subjective narrative. On the other hand, consciousness is the mechanism by which those long-duration archives are read, interpreted, and transformed into coherent stories about origins and causation. Humans are the bridge between scales, tiny organisms of electrochemical impulses who must interpret deep thermodynamic and cosmological processes. Because of that bridging role, the phenomenology of time shapes which parts of the archival record get attention, which questions are asked, and which anomalies are seen as meaningful. Speculation presses further. Could consciousness itself influence the stability of a record? If an observer's active measurement participates in decoherence, then systems designed to be observed might decohere differently than those left unobserved. Practically, the effect is vanishingly small in macroscopic geologic settings. Rocks will recrystallize and isotopic systems will diffuse irrespective of whether there is a mind nearby. The physical community's consensus is cautious. Consciousness is not a magical eraser or restorer of geological inscriptions, but in the context of engineered signals intended to endure across cosmic conditions, the awareness that the format of encoding matters is important. An intentional message hoping to survive eons would do well to exploit robust, environment-resistant encodings, chemical anomalies, deeply buried vaults, redundancies dispersed across many substrates, rather than relying on fragile patterns whose persistence might depend on subtle observer-mediated dynamics. A further philosophical turn concerns the issue of the now. William James called the specious present the short interval in which consciousness holds an array of experiences as a single present. The brain's integration window is neither infinitesimal nor immutable. It widens and narrows with attention, arousal, and age. That window is the local knot where past and future meet and experience. In narratives about deep time, this knot is the place of translation. Records that are legible to minds must be compressed into tokens that can be sampled within the specious present and then bound into narratives across longer intervals. The durability of a message is thus partly about how well it can be chunked into human-scale units of perception. It is no accident that many ancient artifacts use repetitive, low-frequency patterns, rows of marks, monumental geometry, astronomical cycles, all of which are observable across human timescales and can be resynchronized by later observers. The cultural dimension deepens the story. Human social structures externalize time. Calendars, clocks, monuments, and rituals align shared action. Technology amplifies and fragments subjective time simultaneously. Atomic clocks grant precision. Smartphones atomize attention. Cultural pacing changes the way generations relate to deep time. Societies that ritualize long cycles, agricultural calendars, astronomical monuments, cultivate a form of institutional memory that outlasts individual biological memory. This is significant for the question of leaving traces. The more a society encodes time into distributed social systems and into durable artifacts that resist geological weathering, the likelier a message is to persist. Consciousness is not alone in preserving the past. It collaborates with the cultural scaffolding that scales individual memory into collective archives. Where does all this leave the central mystery? Might consciousness play a causal role in the creation of the arrow of time? The measured and thoughtful answer is balanced. Conscious systems do not rewrite cosmological boundary conditions. They do not flip the direction in which entropy grows. The large-scale arrow, the thermodynamic and cosmological asymmetry, is independent of local observers in the sense that it is set by initial conditions and global dynamics. Yet consciousness is the mechanism by which low-entropy patterns are recognized, stabilized locally, and turned into meaningful records. It is the sensitive needle that reads gradients. Conscious agents, by exploiting free energy to create memory, become active participants in the local thermodynamic bookkeeping that gives rise to legible histories. This conclusion reframes priorities. If a listener wants to find traces of deep, ancient authorship, whether natural or intentional, attention should be paid to the ways that living interpreters translate physical correlation into narrative. That means developing cross-disciplinary literacies, geochemistry that knows what kinds of anomalies could survive for millions of years, information theory that quantifies how much redundancy is required for long-term legibility, and neuroscience that clarifies the formats of memory and perception most robust to time. It also means cultivating an epistemic humility about the limits of experience, recognizing that what is vivid to an organism is not necessarily the most persistent signature in the cosmos. The mind is the instrument that interprets the ledger, but it is not the ledger itself. The final image is modest and apt. Consciousness is a lantern that walks along a vast archive, its beam wide enough to read the stones immediately around it and narrow enough that much remains in shadow. Within that lantern's glow, moments are strung into stories. Outside it, the geology and physics continue their patient transformations. To ask whether consciousness makes time is to ask whether the lamp's movement is constitutive of the archive. The pragmatic answer is that the lamp does not create the pages, but it is essential to counting, bookmarking, and telling. The universe writes in many inks: entropic gradients, gravitational waves, isotopic ratios, entanglement patterns. Conscious creatures learn to read some of them. The project for science and for anyone who cares about deep time is not to plead for a special cosmic role for consciousness, but to map, with care and imagination, the formats in which lasting messages can be written and the tools by which living minds can faithfully decode them. In the quiet between one tick and the next, the mind continues its patient work to remember, to predict, and to shape, in small and local ways, how the long story will later be told. What if the last chapter of the universe's biography were not an ending, but an invitation? The question arrives not as a promise of closure, but as a crack through which more questions seep, a deliberate provocation. About scale, about method, and about the ethics of looking. In the long conversation that began with asking whether the cosmos has an author, the conclusion is not a tidy verdict. It is a call to acknowledge both foundation and mystery. Space and time are the stage and the music, yes, but they remain, even at their most familiar, profoundly strange. Across the narrative already sketched, from the nature of space to the possible origins of time, from the accelerating expansion to the paradoxes of holes and horizons, from entanglement to the relativity of clocks, from the plurality of possible universes to the limits of backward causation, and finally to the role of conscious observers, an emergent pattern has formed. The more the archive is examined, the clearer a paradox becomes. Every advance in resolution reveals layers of subtlety previously invisible. Every instrument that extends human reach also enlarges the margin of ignorance. Decoding yields not only answers, but a refined sense of how thin is the surface that human inquiry has scraped. Beneath it, an enormous, patient permanence remains unread. This is an emotional conclusion as much as it is intellectual. It is a feeling of humility that coexists with exhilaration. Humility, because the ledger of the cosmos is vast and often written in alphabets the mind must learn, statistical anomalies, entropic gradients, phase correlations in ancient radiation, spectral whispers of primordial fields. Exhilaration, because those languages can be learned, not as myths to be imposed, but as grammars to be discovered through patient, cross-disciplinary work. The final tone is not despair, it is a steady resolve to widen methods, sharpen interpretation. and to carry forward a moral dimension to inquiry. To close the loop on the themes of the series, the conclusion must walk through several motifs again, but in a spirit of synthesis rather than repetition. First, space as medium and as living fabric. The earlier meditation moved from the Newtonian stage to Einstein's elastic fabric, and beyond into modern suggestions that space-time may be emergent from entanglement or lower dimensional encodings. The practical lesson is layered. On planetary scales, conventional archives, sediments, ice cores, isotopic stratigraphy remain reliable and rich. Miles of sediment are not metaphorical pages, they are physical sequences that can be read with increasing precision. But for the deepest stretches and the most extreme possibilities, the archive is not only matter, but relation. Patterns of correlation across radiation backgrounds, conserved global quantities, and topological invariants become valuable. Instruments must therefore be plural: drills and mass spectrometers for the geologic page, radio interferometers, and polarization-sensitive telescopes for the cosmic wallpaper, quantum-limited detectors, and gravitational wave observatories to eavesdrop on the fabric's tremors. The border between where rocks speak and where fields whisper is no longer absolute, a robust program looks for continuity across media. Second, time, origin, arrow, and locality. If time itself is emergent, then searches for antecedent authorship encounter a metaphysical wall. Before what? If there was a boundary to temporal order, that boundary limits the possible records. Yet theoretical work hints at loopholes. Bounces in quantum remnants may leave statistical fingerprints. Primordial fluctuations stretched by inflation may encode information originating in pre-classical regimes. Meanwhile, thermodynamics remains the practical judge. Records persist only so long as gradients and low-entropy niches are sustained. The conclusion is methodological. Inquiries into deep temporality must combine cosmology's long baseline with the hard constraints of entropy. The most promising signatures will be those that survive both cosmological dilution and geological scrambling. Non-local correlations frozen into the cosmic microwave background, spectral relics of gravitational waves, or invariant balances of conserved particle abundances. Third, expansion and horizons reshape what can be known. Dark energy is not merely an exotic entry in a catalogue. It is an agent that alters the topology of observational possibility. The accelerating stretch of space-time slowly consigns distant eras to inaccessibility. Practically, this generates an urgency to catalogue the universe transparently, more precise maps of large-scale structure, more exhaustive surveys of supernovae and baryon acoustic oscillations, and cross-checked measures of cosmological parameters. Philosophically, it reframes stewardship. If the cosmos isolates regions permanently, then the project of leaving legible traces must reckon with the shrinking audience across eons. Fourth, holes, black holes, voids, and erosive gaps are more than astrophysical curiosities. They are modalities of forgetting. Black holes pose the deepest puzzles about retention and erasure. Their event horizons speak of causal closure, even as quantum theory suggests information may be preserved in correlations. The practical upshot for any attempt at an enduring message is to prefer redundancy and non-local encodings. Signals written only in locally accessible matter can vanish into horizons and be scrambled by mergers. Signals embedded in global invariants or distributed across many degrees of freedom stand a better chance of being recoverable in principle, though perhaps not in practice. Fifth, entanglement rewrites the vocabulary of proximity. If spatial adjacency is, in some formulations, the macroscopic consequence of entanglement patterns, then the notion of a place that stores information becomes relational. This opens daring possibilities. An author concerned with permanence might prefer to encode messages in non-local, topologically protected forms rather than in brittle monuments. It also creates experimental demands. The search moves from purely geological archaeology to a new kind of information archaeology, hunting for statistically significant non-classical correlations across disparate datasets. This requires instruments sensitive to phase and coherence, and it requires statistical practices that can separate genuine non-local signatures from selection effects and noise. Sixth, the relativity of time and the plurality of frames demand translations rather than absolute datings. There is no single cosmic metronome that all observers share, but there are multiple practical anchors, pulsars, the cosmic microwave background, spectral lines that can be used as shared reference points. Practical encoding for deep time will lean on such anchors, embedding temporal information in relational terms. tie a Mach to pulsar phases, to a CMB temperature, to a set of invariant atomic transitions. The art of durable time-stamping is therefore a craft of redundancy and cross-calibration. Seventh, the multiverse widens the conceptual horizon while narrowing practical expectation. If other domains exist, many histories may forever remain inaccessible, and the hope of an encyclopedic paleography of everything that ever happened collapses into a more modest program. Map and interpret what lies within causal reach. Still, the multiverse suggests valuable heuristics. If signatures must be robust across vacua, they will probably be topological or algebraic invariants, or they will be encoded in modes of fundamental fields that transcend local compactification choices. Those are speculative but coherent design principles for messages intended to survive across cosmological contingencies. 8. The limits of backwards causation and time loops are severe. The physics permits fascinating mathematical possibilities, but thermodynamics, quantum back reaction, and realistic energy conditions curtail the plausibility of macroscopic time travel. The archive remains essentially one-directional. Records are written forward and, in most practical senses, cannot be rewritten by later actors into an earlier epoch. This realization is both restraint and a safeguard. It preserves the moral weight of history and demands that attempts at remediation or warning reckon with physical impossibility. Ninth, the human mind is neither passive ledger nor sovereign author. It is a specialized reader and a limited scribe. Consciousness does not create global time, but it shapes which features of the archive are noticed, encoded, and transmitted. The subjectivity of temporal experience informs institutional choices about what is preserved. Calendars, rites, monumental architecture, and databases become the cultural scaffolding that extends individual memory into something potentially enduring. Task of preserving legacy is therefore as much social and ethical as it is technical. Societies must choose what to encode and why, recognizing the asymmetry between immediate usefulness and deep durability. Taken together, these motifs yield practical programs and moral injunctions. Practically, the effort to read the deep ledger must be plural and patient. It requires investments in long-term observatories, in geological archives, in quantum-limited detection technologies, and in computational infrastructures for data curation and cross-correlation. It means building repositories that avoid single points of failure, distributed vaults of chemical markers, deep freeze archives of digital and analog records, and redundantly encoded messages across electromagnetic, gravitational, and perhaps particle channels. It also means cultivating analytic disciplines capable of handling high-dimensional correlation claims, information theory, Bayesian statistical frameworks, model selection protocols, robust to selection biases, and clear standards of significance that resist the seduction of narrative. Methodologically, the community of inquiry must practice humility. Absence of evidence should be interpreted cautiously. A null result does not prove non-existence, it refines probability distributions and constrains models. Bold hypotheses must be pursued, but with sober testing rather than wishful pattern recognition. The best science in this domain will be interdisciplinary in the literal sense, cosmologists speaking with geochemists, quantum information theorists, dialoguing with paleontologists, statisticians partnering with philosophers of science. Ethically, there is a responsibility in asking about permanence. To imagine encoding messages for far futures is to make choices about what ought to be signaled and why. Should a civilization broadcast its triumphs, its warnings, its mathematics? Who decides? The prospect of writing into the planetary or cosmic substrate carries consequences for other beings, whether human descendants or unknown future intelligences. Some proposals for long-term messaging skirt this ethical terrain. The wiser path recognizes it. Stewardship demands not only technical resilience but moral reflection about legacy, consent across generations, and humility about the right to alter environments in ways that may outlast present communities. Finally, there is an aesthetic and existential last word. The more the universe is interrogated, the more it yields the sensation of a thin veneer of permanence spread over an immense unknown. Decoding increases awareness of how much remains under that veil. Each drilled core, each spectral map, each gravitational chirp is a new aperture through which age and process are glimpsed. Yet each aperture also enlarges the sense of scale, reminding observers that their instruments read only a sliver and that the unread bulk of eternity is patient and extensive. This realization is not paralyzing, it is galvanizing. To stand with a spectrometer in hand, or to listen with a kilometer scale interferometer, is to join a tradition of persistent curiosity that respects limits without surrendering ambition. The narrative offered here concludes not with an answer, but with a stance, an elective modesty. The cosmos is both archive and mystery. Space and time are foundations and riddles. The act of decoding is not a reductive triumph over ignorance, but an ongoing apprenticeship in translation, an exercise in reading, verifying, and iteratively refining models in a universe that will always keep more than it gives. And so the final image is both fragile and vast. Imagine the thin crust of a planet, a fragile envelope of rock, ice, and water, annotated by transient voices, fossils, and stone. A faded inscription of isotope ratios, the faint radio signature of a civilization long gone. Now lift the view to a scale where the planet is a mote in a network of fields and correlations, nested in a vast web of entanglement, dicey with horizons and swept by an expanding darkness. At each scale, the ledger is different. At each, different languages are required to read it. The paradox persists. The more is known, the more the depth becomes apparent. The more the text is deciphered, the more its margins recede. That is the last lesson, and the first commandment for those who listen to deep time. Space and time are foundation and mystery, simultaneously the medium that makes records possible and the thing that most threatens their survival. The more the archive is decoded, the clearer it becomes that observers have touched only a thin shell of eternity. Beyond that shell lies an infinite frontier, not a blank to be conquered, but a patient expanse that invites respectful curiosity, rigorous method, and ethical stewardship. The work of reading the universe will outlast individual lifetimes and institutions. It is a civilizational practice of patience, discipline, and wonder. In the end, discovering an author, or deciding there was none, will be less a single revelation than a slow sedimentation of evidence, a layering of careful instruments, robust arguments, and collective humility pressed into the strata of knowledge. That sedimentation, more than a final proof, is the kind of legacy worth leaving.